When I see area, I think integration. When I see these curves, I think I should draw a picture, so let's draw a picture. I've got the curve y equals square root of x. That looks something like this. This is my x-axis, this is my y-axis. I've got the line y equals x minus 2, so that's 0 when x is 2. I like making things zeros, and then it's got gradient 1, so it's going to go up like this. I suppose intersect this square root curve somewhere, and the x-axis. So I have a bit of the x-axis as well. So I think they're asking for this area here. Now, to find areas under curves, I can use integration, but I've got to remember that that finds the area between the curve and the x-axis, which is not quite what I want here. So, for example, if I integrated square root of x from 0 up to here, then it would include this triangle of area as well. I mean, that's not a problem because I know the area of a triangle, I can subtract it afterwards, but I need to remember to do that. Okay, I also really want to find out where this point is. Let's do that now. So let's try and solve root x is x minus 2. That's going to give me x is x squared minus 4x plus 4. I'm going to rearrange that to get x squared minus 3x plus 4, which is x minus 2, x minus 1? No, what have I done wrong? 5, which is x minus 4. There we go. Maybe I should have guessed these roots earlier. The square root of 4 is 2, 4 minus 2 is 2, so this is the point 4, 2. 4, 2. Okay, and this point was 2, I said. Okay, so here's my plan. I want to integrate the square root of x from 0 up to 4, and then subtract this triangle area. That triangle area is going to be 1/2 base times height. Base is 2, height is 2, so I just need to do this integral and subtract 2. Okay, integral x, the square root of x is the same thing as x to the 1/2, so this integral is going to be x to the 3 over 2 times 2/3. Put the limits in, 4 and 0, subtract that 2. 4 to the 3/2 is 2 cubed is 8, 8 times 2 is 16 over 3. Okay, I'm going to get 16 over 3 minus 6 over 3 is 10 over 3, so that makes my answer D. Okay. (1b). This is the first maths question that I ever wrote. It's based secretly on my PhD research. I'll tell you more about that at the end. So let's do the question first. It tests two things. Do you know what the derivative of e to the kx is with respect to x? And also, can you solve equations once you've plugged that in? So all the question's asking us to do is to take this function, y equals e to the kx, and check whether or not it satisfies this equation. So to try and simplify this equation, we need to plug in y in here and just find out whether it works or not. Probably there'll be some special values of k where maybe this does work. Okay, and it's our job to find those special k values. Right, so the derivative of e to the kx is k e to the kx. This was a new fact on the syllabus for 2018, so I was keen to get it into the mat. And then the second derivative will be k squared e to the kx. That is, I suppose, an adaptation of something on this syllabus that I'm testing here, whether you can differentiate e to the kx even with some constant out the front. Of course, the constant out the front doesn't make much difference when you do the derivative, it just stays out the front. Right, okay, so armed with this derivative and this second derivative, I'm going to plug them in and see if it works or not. Okay, so k squared e to the kx plus k e to the kx. dy by dx is k e to the kx minus y is e to the kx equals e to the kx. Dy by dx is k e to the kx. So here's what I want this to be true. Now, in general, these equations would be really horrible, but luckily, each side is a multiple of e to the 2kx, or e to the kx twice. And e to the kx is not 0. That exponential is definitely positive. So I can divide both sides by e to the kx twice, I suppose, to get k squared plus k minus 1 is equal to k. So I've divided by e to the kx twice, this bracket and also this bracket. Okay, looking pretty good. I've now got k times k plus 1, k minus 1 is equal to k. So this is looking pretty good. I could say k equals 0, or, so being careful, I'm about to divide by k, or difference of two squares, I suppose. K squared minus 1 is 1, so k is plus or minus root 2. K could be any of these three values. K could be 0, or root 2, or minus root 2. Those all work. K equals 0 gives us a slightly funny function, function y equals 1, but that works because I suppose this bracket is 0 and also this bracket is 0, so that solution does work. And root 2 and minus root 2 are just special values of k you can put in there that make this work. But all three of these values of k make a function y equals e to the kx that satisfies that equation. So the answer is D. So this process of trying the function e to the kx is secretly a Laplace transform, except somehow this equation is too difficult to really solve with Laplace transform. So what we're doing here is trying a sort of lucky guess of function. It's inspired by some really horrible differential equations I had to solve in my PhD, where the way I solved them was to just guess a function and try and find a solution. So that was where I got the idea for this question from. Answer is D, 3 distinct values of k. Okay, 2018 question 1c. This is a question about parabolas. There were strangely quite a few questions about parabolas on Maths 2018. This is one of them. So we're given two curves, y equals ax squared plus c, that's some parabola, and y equals bx squared plus d. And we're asked when they've got exactly 2 points of intersection. So points of intersection would be points with the same x and y values. So I suppose I'd have simultaneous equations. Ax squared plus c, y equals bx squared plus d. This is how I like to think about points of intersection for curves where I'm given the equations of the curves. I like to think about them algebraically. So here I'd start trying to solve these to find out whether I could find exactly 2 points of intersection, exactly 2 solutions. So if I solve these, these y values will be equal at the point of intersection. So I want this to be true. And then rearranging this, I suppose I want d minus c equals a minus b x squared. So, provided a minus b is not 0, if a minus b is not 0, then I can divide. I can do x squared is d minus c over a minus b. And that's going to have exactly 2 solutions, provided this thing is positive. Okay, so 2 solutions for x if d minus c over a minus b is positive. Okay, and I suppose that I also need a minus b to be non-zero, a not equal to b. Okay. That's not any of the options in the question, so I need to do a little bit more work. Let's just think carefully. So these 2 solutions for x will have the same value of x squared, so they'll have the same value of y, but that's okay. There'll be 2 different solutions, sort of plus or minus x points, I suppose. There's some symmetry to these parabolas. Maybe if I was thinking about this geometrically, I'd have already spotted the symmetry. Okay, I want d minus c over a minus b positive. That looks a bit like this expression over here. And in fact, if a is not equal to b, then I could combine my factors together. I could multiply up by a minus b squared. So this is true. Equivalently, d minus c times a minus b squared over a minus b positive. So I've multiplied both sides. Oh, excuse me, there's over a minus b just behind my head. These are equivalent because I've multiplied up by a minus b squared, which is a positive thing, not 0. So I precisely want d minus c times a minus b to be positive, which is option E. Okay, let's do a quick geometric approach as well, just to see what that looks like. So the curves ax squared plus c, there's going to be something like this, perhaps, and the curve bx squared plus d might be something like this. So we can see that if the parabolas are like this, with C bigger than D, and A positive and A positive and B negative in my picture, there's no points of intersection, which is quite bad. I suppose what I want is, if D is going to be less than C, then this parabola, if D is less than C, then I want this parabola to grow faster than the one above. Want bx squared plus d to grow faster so that it catches up with the ax squared plus c parabola. So I would want b to be bigger than a. Okay, that's one possibility. Or I could have them the other way round. I could have, if c is less than d, then I want a to be bigger than b. Okay, so what these inequalities now say, that I would need some way to combine these together into one statement that's true in each of these cases. And I suppose what I've got is, I've got the cases, my second case here is d minus c is negative, and a minus b is also negative, whereas over here I've got d minus c as positive, and a minus b is also positive. So the product is going to be positive in both cases, and actually that's precisely the case in E, right? If this thing is positive, then either both terms are positive or both terms are negative. So I could perhaps have reached E through some geometric argument like the one I've shown on the left there. Okay, that's Map 2018, question 1C, the answer is E. (2018) question 1D. This is a question about transformations of curves, and you've got a choice. You could find, I suppose, the minimum of f of x first and then think about the translation for the coordinates of the minimum, or you could find the new curve after the transformation and find the coordinates of the minimum that way. I'm going to show you both methods, and you might like to think about which method you used when you attempted this question. Okay. If you haven't attempted the question yet, then I advise you to go and have a go at it now before I finish doing the question. I'm going to complete the square on f of x. That's how I feel like finding the minimum today. I could differentiate it. Right now I feel like completing the square. That's going to be 25 over 4. I'm going to need to add on another 3 over 4 to get up to 28 over 4. So f of x has a minimum at 5 over 2, 3 over 4. This square is minimised when it's 0, when x is 5 over 2. I love making things 0. And at that point it takes the value 0 squared plus 3 over 4. Okay, so y equals f of x minus 2 is translated 2 units to the right. So this is the same, the curve has been translated 2 units to the right, so the new minimum will be at, I need to add 2 because it's been translated 2 to the right. It's going to be 9 over 2, 3 over 4, which is option B. Let's quickly do it the other way by working out the equation of the transformed curve and then finding the minimum. So f of x minus 2, maybe you read the whole question, you got to here and you thought f of x minus 2, I should work out what that is. Well, that's x minus 2 squared minus 5 times x minus 2 plus 7, which is x squared minus 4x plus 4 minus 5x plus 10 plus 7, which is x squared minus 9x plus 21, which has a minimum at, completing the square again because I'm still in the mood to complete the square, x is 9 over 2 plus, I've got 81 over 4 versus I want 84 over 4, so I need to add on 3 over 4. What a surprise! The new minimum is at 9 over 2, 3 over 4, because it's 9 over 2 that makes this square the smallest when it's 0, and then 0 squared plus 3 over 4 is 3 over 4. So the answer is still B. Happily, it's B with either method. So if you've had a go at this question, and I hope you had a go at this question, then maybe think about which of these methods you used, and if you've seen the other method for the first time, maybe think about whether that method might suit your style more, or whether you'd like to explore doing questions with the other method sometimes as well. Okay, Math 2018 question 1E. This question's a little bit more unfamiliar. There's almost nothing in the question that you might recognise from A-level maths or equivalent, but we're going to need to draw some sort of picture again. We're used to drawing pictures of geometrical problems like this, and we're going to have to think about distances to think about whether things are inside a circle or not. Okay. So, a circle of radius 2 is centred on the origin. Let's try and draw that. What a lovely circle. There we go. 2 minus 2. Is drawn on a grid of points with integer coordinates. Okay, so I can see some points with integer coordinates. Integers are whole numbers, positive or negative. I can see some points that are definitely inside this circle. And the question is, are there any others? Is, for example, this point inside the circle? So that's the point 1, 1. I guess I need to work out the distance from the origin. The distance there from the origin is going to be root 2 by Pythagoras, which is less than 2. So yes, this point is in the circle. And by symmetry, I suppose these ones are as well. Some nice reflectional symmetry going on. I haven't thought about the question yet. I'm still trying to count the grid points inside the circle. It says let m be the number of grid points that lie within or on the circle. So I need to think about ones that maybe lie on the circle as well. I don't know if we're going to find any of those. I think I'd like to think about the point sort of 2, 1, but I'm pretty sure that's not inside the circle because it's definitely further away than 2, 0. So what's that? The distance from origin there is going to be 4 plus 1 is 5, root 5, excuse me, which is bigger than 2. So these points are not inside the circle. And there's quite a lot of them because of all the symmetries of a circle, I suppose. Okay, other points I need to think about? Well, not really, no. I mean, I could start thinking about further away points, but I'm not really sure I want to. So we could look at 3, 0, that's definitely not in the circle. We could look at 2, 2, it's just ridiculous, it's definitely not in the circle. 2, 2 is a distance 2 root 2, which is much, much, much bigger than 2. And 3, 0 is at a distance 3, which is incredibly large. Right, okay. What are we doing? So n is the number of grid points that lie within or on the circle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, n is 13. What is the smallest amount the radius needs to increase by for there to be... Oh, and then how many points are we asked for? We're asked for 2n minus 5. Okay, so 2n minus 5. I've got to work out 2n minus 5 is 26, minus 5 is 21. So we're asked for 21 grid points within or on the circle. Okay, 21 is an extra 8 points. How am I going to pick up an extra 8 points? Well, I can see some candidate points. Not the one that's at 3, that's miles away. But there were these ones at 2, 1 and 1, 2, and symmetry around here as well. There were those 8 points that were pretty close to being inside the circle. If I increase the radius just a little bit, smallest amount the radius needs to increase by, and it's within or on. So if I increase the radius enough that these points are on the circle, then I'll pick up an extra 8 points. Okay, how do I do that? Well, I need to make the radius... I want these points. So I need to make the radius root 5. To do that, I need to increase by... It's currently 2, root 5 minus 2. Okay, so my answer is A. Okay. I think the slightly strange thing about this question is the n in the question is just the number 13. And that's something you work out by drawing a picture. Okay. (2018) question 1F. This is a question about a particle moving in the xy plane. And it's going to move taking turns. I suppose moving, here we're thinking of it starting in one position and then moving sort of discretely. Like a chess piece moving on a chessboard. You take turns and the pieces move. And it's got 2 possible moves that it can make. It can move 2 to the right and 1 up. So if it's here at some coordinates, then it could be moving 2 to the right and 1 up, which is a translation by the vector 2, 1. Or it can move 1 to the right and 2 up. So that's a translation by the vector 1, 2. Okay, and we're not told how these moves are chosen, so it could do either of these moves in any order, I suppose. We're asked for the closest that the particle might come to the point 2575. Maybe it's possible that the particle can reach that point, in which case the closest would be 0. Maybe it's the case that you can only get within a certain distance of this point, though, no matter what sequence you choose these moves in. And in fact, that second case is the answer to this question. You can't actually reach this point by making these moves. To see why, let's think about the most extreme possibilities of what you could do. So if you choose the first move lots of times, and you move like this, I suppose like a knight in chess, but we're not allowed to move backwards, so I think no chess theory is helpful here. If you keep doing the first move, then you'll move along the line, I suppose that's the line y equals, what's that line? Y equals x over 2. And if you do the other move again and again, then you'll move up like this along the line y equals 2x. And if you alternate moves, or if you do something else using some of each of the moves, then you'll do something in between. So maybe our particle moves like this way first, and then moves up like that, and then moves like this again. It's going to stay though somewhere in that wedge, that kind of cone of possibility of where it could be. Because at each stage the angle of its motion can't exceed what it would be if you just did the maximum angle each time. Okay, so it's going to wander around somewhere in between those two lines. Here's the crucial fact: the point 2575 is not inside this cone of possibility, so it's impossible for us to actually get to the point 2575. It's up on the line y equals 3x, so it's somewhere up here in my diagram, I suppose, not to scale anymore. So we can't get to the point 2575, but we'll get close if we're on this line, if we're on the line y equals 2x. So we hit all of the integer points on the line y equals 2x. I think that's true. Yes, we move 1 across each time, going up 2. So we hit all of the integer points on y equals 2x. And I suppose we want to find the closest one of those to this point. Okay, let's try and do some geometry to work out where that closest point is. Okay, so I'm thinking about the line y equals 2x, and I want to find the closest point to 2575. Okay, so really I want to drop a perpendicular to find that closest point. Now my closest point is, my perpendicular is going to have gradient minus 1 over 2x. I don't know where it is up and down, so this line here is going to be y is minus a half x plus constant. I don't know what the constant is. Oh, I suppose I know that this normal, I've dropped this perpendicular from 2575 to the line. I know the gradient because it's perpendicular, and I know that it goes through the point 2575. So I know that 75 is equal to minus a half times 25 plus c. So my constant is going to be, something like, what is that? 12 and a half, 87 and a half is my constant. Okay, so that's my normal. Now at this point, I've put a half here, and I'm worried that this point this point where the perpendicular meets the line might not be an integer point. It might not be a point that the particle can actually get to, but I'll look at nearby points. This should give me a good idea of what the nearest point might be. It's going to be near to the nearest point, I think. Okay, let's find out where this line intersects with y equals 2x. Let's find out point of intersection. So point of intersection would have y equals 2x, and also y is minus 1/2 x plus 87.5. So if I try and solve those, then I'll get 2.5x is equal to 87.5. So x is going to be equal to, oh, I want to do 87.5 divided by 2.5. That's 40, take away 5 is 35, I think. Quick check, 70 plus 17. 2 is 70, half of that is 17.5, 87.5. X is 35, y is 70. Okay. And actually that isn't a whole number point, that is an integer. Those are whole numbers. So at this point it's something we can get to, and it's the point where the perpendicular meets the line y equals 2x. Okay, so this is looking pretty good as my candidate for the closest point. Let's work out its distance. To do that distance I need to do 5 squared plus 5 squared square rooted, for Pythagoras reasons, which is going to be 25, 25, 50, I suppose that's 2 root 5, which is not one of the options. Thanks for watching. 10, 20, what am I doing wrong? 5, that's 10. To find that distance I need to do the difference between here, which is 10 squared plus 5 squared square rooted for Pythagoras reasons. That's 125 square rooted, which is 5 root 5, which is option B. So that's my closest point. It's a point I can get to. It's nice and close to 2575. Actually, because of the options, I know that there isn't a closest point, so I don't need to worry too much. I know that you definitely can't get to the point 2575, and I found a point that's only a distance 5 root 5 away. Okay. (2018-1G) is another question with some parabolas in it. So let's do some parabola maths. We're looking for a value of c that makes these two parabolas touch, so meet tangentially at a single point. Okay, so I suppose I want these curves to have a kind of single root or single solution. Okay. So my first idea was to sort of plug one of these into the other to look for x squared plus c squared equals x, one solution only. And that's quite tough because this is a quartic equation. I can't really see a way in. It doesn't have an x cubed term, but it's still a fourth order polynomial. I don't know how to solve those off the top of my head. I can't see any obvious roots in terms of c, so I don't know what to do there. Maybe I should be thinking about this clue they give me in this question to think about tangentially. So meeting tangentially at a single point. I suppose let's draw a picture. Maybe I should have done that first. Y equals x squared plus c looks like this, and y equals root x. Or sorry, this is y is plus or minus root x. There's a parabola this way around. Looks like this. So I want them to meet tangentially. I suppose that means they'd have the same gradient there. So I've got y equals x squared plus c, y squared equals x. That didn't seem to get me anywhere by just setting those equal to each other. I mean, I want them equal to each other, but I can't immediately solve that for x or c or anything. I've got this extra condition though. I want them to have the same tangent line at that point. So I want these to have the same gradient. What are they? Well, so the gradient of this one is just 2x, and the gradient of this one, where y equals x to the half on this top bit, the gradient of that, I've written it as x to the half because I want to differentiate it, and I can differentiate x to the power, is 1/2 x to the minus 1/2. Okay, so this is pretty great because I want these to be equal, and I'm saying pretty great because this doesn't involve c anymore. So somehow this is an easier condition to satisfy, or an easier condition to work with. I want 2x to be 1/2 x to the minus 1/2. It doesn't have any c's in it, so I can just go and solve this, right? That's x to the 3/2 is equal to 1/4. So x is 1/4 to the 2/3. Something like that. Anyway, right, okay, let's take my value of x, 1/4 to the 2/3. Do I believe that? Quick check. 2x, 1/2, x to the minus half, 4, x to the minus 3. Yeah, okay, I'm going to stick with that. X is 1/4 to the 2/3. I'm going to plug that in over here, because I do want these not just to have the same tangent, but to have the same y coordinates. at that point. Okay, so when x is 1 over 4 to the 2 over 3, I want these things to be equal. Which form am I going to work with? The one with it multiplied out or the one with it not multiplied out? I think I'm going to work with the one with it not multiplied out, which is going to be 1 over 4 to the 4 over 3. Laws of indices to square this thing. Here's what I want, 1 over 4 to the 2 over 3. Okay, which it looks to me like an equation for C. It says that I should be trying to solve this for C. And that's actually the direction the question is going in, right? The question wants us to think about what the value of C should be. Okay, so now I'm going to solve this equation for C. There's a plus or minus sign in here that I should maybe worry about. I want C to be positive for my picture to make sense, I suppose. So I think I'm going to take the plus square root as I solve this equation. If I take the minus sign, then I think C ends up being negative, which I don't want. Okay, does it tell me C is positive? No. Okay. Maybe C being negative is just a bad idea. We should check that separately, I suppose. So C should be then, this is 1/4 of 1 over 4 to the 1 over 3, so this is 3/4, 1 over 4 to the 1 over 3, which is 3 over 4 cube root of 4, which is option B. Just a little worried there about C being negative. Let's explore that other route. The alternative here was that C is minus 1 over 4 over 1 over 3 minus 1 over 4 to the 4 over 3, which is something like, so that's instead of this being 1 over 4 to the 1 over 3 minus 1 over 4 to the 1 over 3, that's minus 5 over 4, 1 over 4 to the 1 over 3. Let's think about whether that works or not. So that's giving me the value of C somewhere down here, which doesn't feel right somehow. It feels like this would be like this, and my parabola would be like this, and I think I can see what's happened. I think this would have the value of y being negative, right? Because then C plus 1 over 4 to the 4 over 3 would be some negative number. That's my C plus x squared is negative y, but I assumed in here that y was positive somewhere. Okay, so this negative point over here is actually an intersection with y being minus square root of x. So if I want this solution up here, I have to take y as square root of x. This solution spat out with C negative is actually thinking about minus square root of x. Okay. There's a sort of trap in this question that lots of the actual positions of things don't matter. We're going to approach the question now and I'll point out the things that don't matter. So there's two triangles, S and T, they're in a circle. We're not told where these corners are. We're told the areas are S and T, and that S is the smaller triangle, so that S is less than T. And we're asked to find the smallest value of some algebraic thing. The trap is to write down positions for all the points, to write down equations for lines, to write down expressions for the areas, S and T, in terms of the positions of the points. What this question is really testing is whether we can think geometrically, and whether we can think about what happens as we vary the positions of these points. All we're told is that S is less than T. We're not given any other restrictions on what these triangles might be. So we can imagine moving the points around and thinking about how that changes S and T. If you do that, I think you spot quite quickly, I hope, that if you keep most of the points still, that's the easiest thing to do when you're moving points around, but you move, let's say, this one around the circle, we're not told where it is, so it could be anywhere around here, then you can make the area of the triangle very, very small as this point gets down here. So S could be almost 0. Probably not actually 0, because then it's probably not a triangle. But S could be almost 0. It could be any number between 0 and it could be any number between 0 and something, where I don't want to think too hard about what the area of this particular triangle is in here. Similarly, t could be, I suppose, any number. We can move t around here. Do I mean any number? Yeah, I suppose this circle could be really big, it could be really small. We're not told the radius of the circle either. This point could be somewhere over here. In the diagram, t is a really huge triangle, but this point could be over here, in which case t would be quite a small triangle. So t could also be almost 0. I suppose the radius of the circle could just be really small, so that these areas are pretty small. Okay, t could also be almost 0. We're told that t is bigger than s though. So I suppose the biggest that s could be, theoretically with this limit, is that s could be equal to t, or just slightly less than t, not equal to t. That's actually possible if the points between s and t are something like a diameter. If that's the case, and oh no, what do I want? So I want maybe the line could be some sort of diameter, and s and t could be like this, with s slightly off the midpoint of that arc, so that s is less than t, but they're pretty close together. So s could be almost t. And actually, anything else is possible. With a diagram like this, I could move s, I can move this point around, so that the size of the triangle s is anywhere between 0 and the size of the triangle t. I mean, the only reason I'm not making it bigger than t is because they've told me that s is less than t. You could make versions of this picture with s being the big triangle, or s being very small, or s being exactly the same size as t. This is the only restriction on which pictures we're considering today we've been given. Once you've realised that, the geometry of the problem, the kind of circle and triangles, doesn't matter at all. What we've realised is that s and t could be any numbers with 0 less than s less than t. Okay, so they could just be any real numbers. So long as we've got 0 less than s less than t, then we can draw a picture that's an example of s having the small area, t having the big area, the areas matching up with little s and little t, and then that'll be an example of two triangles inscribed in a circle. Okay, so the actual question asks us to find the smallest value of this expression. And now we know that s and t could be any numbers at all. We're just trying to minimise this expression for any values of s and t. When I see something like this that's a quadratic divided by, it's a sort of a quadratic in s, sort of a quadratic in t, and st is kind of two terms as well, it's like a cross term. It's sometimes helpful to split that into separate terms, to divide top and bottom, I suppose, or to think about this being 4 over 5 s over t plus, and this t squared over 5st would be t over 5s. That's sometimes helpful because now when I look at it, it looks like it's something to do with s over t, t over s. Maybe that's a helpful way of thinking about it. So, for example, if I can make that point more clearly by saying something like, let u be s over t. Now, we've seen that that ratio, s over t, could be anything between 0 and 1. It could be pretty close to 0 if s is pretty close to 0 and t is not. Or it could be as big as 1 if s is almost as big as t. Then this ratio, s over t, could be almost as big as 1. The thing I'm trying to find the smallest value of, goodness me, is 4 times u plus 1 over u. Okay, with u between 0 and 1. And now this looks more like a maths question, because now this is asking me to minimise this expression in terms of u for a particular range of values of u. Okay, I'm going to do that by differentiating. I'm going to differentiate this expression. I'll get 4 minus 1 over u squared. That's equal to 0. I'm differentiating with respect to u, and that's equal to 0 when u is equal to 1/2. I think, yes, when u is 1/2. When u is 1/2, I'll have value of this thing will actually be 2 plus 1 over 1/2 is 2, which is 4. I've missed a 5 somewhere, haven't I? Yes, I've missed a 5 in here and in here. Okay. When I differentiate it and set it equal to 0, I can multiply 3 by 5, and this will still be 0. Okay. That's still minimised when u is 1/2, in which case the value of this expression is 2/5 plus 2/5, which is 4/5, making the answer C. And you might make this smallest value by making s and t very close together, very almost equal in size. Okay. Oh no, by making s 1/2 the size of t. Whoops. Right. Okay. (2018) question 1I. This is the sketch of some horrible curve, my word, and it's in one of these pictures. The question is, which one? All of the pictures to me look like two parabolas, which is pretty suspicious. I'd get two parabolas, I suppose, if something factorised into a pair of parabolas. So the question is to stare at this thing they've given us and try and recognise it at all. So at first it looks very scary and unfamiliar. Eventually I spotted this 1, 4, 6, 4, 1 pattern. I'm saying 1 for the bits that don't have numbers. Those are the numbers from binomial expansions. So this looks like something's been binomially expanded. The next question is, what's been binomially expanded? This y to the 4 makes me think that a y was involved. The 461 is making me think of a power of 4, so this y to the 4 is looking like, yeah, something's been raised to the power of 4. This x to the 8 is making me think x squared, so my guess is going to be that this is x squared plus y to the power of 4 inside the brackets. I've noticed there's a squared over here as well. So yeah, let's just think x squared plus y to the 4 is x to the 8 plus then 4, x to the 6, because that's the cube of the first term, y, and then yes, the x's go down by 2 each time, the y powers go up by 1 each time, 1, 4, 6, 4, 1. Brilliant. Okay, right. I need to remember that all of that's squared and equal to 1. Okay, so I've got x squared plus y to the power of 8 is 1. Okay, so there's two possibilities for what this could be. If you raise something to the power of 8 and you get 1, then either the thing was 1 or it was minus 1. Anything else you raise to the power of 8 tends to go quite badly wrong. Okay, badly wrong in the sense of not getting the number 1. Right, so let's rearrange these. This is 1, y is 1 minus x squared, and this is y is minus 1 minus x squared. So those are both unhappy quadratics, I suppose. 1 minus x squared looks like this, minus 1 minus x squared looks like this. That makes, I think, the picture look like C to me, which is a picture of two parabolas with different y-intercepts, and both of them are unhappy parabolas. Okay. (2018) question 1J. This is a very strange question. It asks us for sketches of the curve p of x plus p of y equals 0, where p is some polynomial, and there are so many polynomials, there are so many to think about. What we're actually asked is, here's some sketches, which ones could be the sketch of p of x plus p of y equals 0 for some polynomial p? And that's a very difficult question because there's lots of possible things we could sketch for different polynomials. Some of them are very hard to sketch, and even if we sketch a whole lot of them, we might miss a few, and we might miss some that correspond to some of these pictures. So it's a pretty hard task. Let's try some examples. So the first polynomials I want to check. Well, I mean, the first thing I thought of when I was looking at this and looking at the options was something like x squared. So if my polynomial is x squared, then this expression reads x squared plus y squared equals 0. Unfortunately, that graph is not C. That's the circle with 0 radius, which is just the point at the origin. satisfies x squared plus y squared equals 0. So there's a bit of a head scratcher. And what I wanted was x squared plus y squared equals 1. I was hoping that I could get like a circle out of this. And after thinking a bit about other curves, so having thought about x squared, I thought about x squared plus ax plus b or something, and the extra x's made this more complicated than I wanted it to be, I suppose, because putting it together, right, that'll be x squared plus ax plus b plus y squared plus ay plus b is equal to 0. All of these are polynomials, all of these are part of the question because they're all different polynomials p. Think about the sketches, the curves. Who knows, maybe if I choose a and b right, this might be something like one of those. Okay, what is this? This is the circle x plus, I suppose I can write this as x plus a over 2 squared plus something like b minus a squared over 4 plus y plus a over 2 squared plus b minus a squared over 4 equals 0. This is a circle with centre minus a over 2 minus a over 2. So maybe I should try a equals 0. Try a equals 0. So that it's got centre 0, 0. And if I put a equals 0 in, then I've got this constant plus b plus b. So maybe I should try b is minus 1/2. If I put in b is minus 1/2, then I could move these minus 1/2s over to the other side. And then I would get x squared plus y squared equals 1. So x squared plus y squared equals 1 is an example of, for the particular polynomial, p of x is x squared minus 1/2. That gives you a circle. I'm pretty sure this is a picture of a circle. I'm going to say that C, yes you can. So what does that give me? I think you can make C. That gives me not A, because A says C cannot be done, and not B, because that says C cannot be done. These are still in the running. Okay. So after a lot of work, I've managed to make this circle. Then I thought a bit, I suppose, interesting point, I haven't made, is this a parabola or something? I haven't made one of these. I tried x squared sort of quadratic stuff in there, and I got circles, not parabolas. Okay, so it's kind of interesting, but maybe I'm not trying hard enough. Maybe if I try harder, I'll get parabola. Next thing to try is probably straight lines, polynomials. So maybe I should try p of x is mx plus c or something for a polynomial that's just got a constant term and a linear term. If I do that, then this expression reads mx plus c plus my plus c equals 0. If m's not 0, I can divide that by m. Maybe I could just choose to. So this looks like the equation of a straight line. Y is minus 2c over m minus x, which if I take c, if I take m is 1 and c is 0 or something, then that would be the line y equals minus x, which looks like d to me. Okay. So a nice simple polynomial over here, p of x equals x. I think that gives me a straight line y equals minus x. So that looks like d. That rules out this option, I think. So I'm left with these ones, which require me to think about A. Strangely, they do not require me to think about B. This kind of triangle shape. I'm just really not sure how I'm going to get sharp corners off this, by the way. This has got all these sharp corners. The curves I've sketched so far don't have sharp corners. So something I've spotted back up here when I was working with quadratics and thinking about circles was that normally when you get the equation of a circle, you can put the circle where you like. You can have the centre being somewhere with an x coordinate and a y coordinate. But here I had the same x coordinate and the y, same x and the same thing turned up in x and y. A over 2 in both of these. That's not a coincidence. That's because it's the same polynomial on the x and the y terms. So whatever I do with my polynomial, it's sort of treating x and y the same. That's making a curve like this look a bit suspicious. How am I going to do that if I'm treating x and y the same, how am I going to build a shape like that? In fact, we can think of this as some sort of symmetry. So we can think of this as, think about what happens. What if I swap x and y? So swapping x and y would be taking a point on this curve, so a point maybe over here with some values of x and y, and looking at the point with x and y coordinates the other way round. So if you swap the values of x and y, if this is 1, I said it was radius 1 earlier, but never mind. If this is 1, 2, then I'd be claiming that p of 1 plus p of 2 equals 0. But if p of 1 plus p of 2 is 0, then also p of 2 plus p of 1 is 0. Kind of obviously, you could swap these two terms around. So then 2, 1 would have to be on this curve as well. What I'm getting at here is that that's a reflection in the line y equals x. And starting with a point and doing this swap, I should get a new point on the curve. So this should be a symmetry. Symmetry of the curve. Because it's treating x and y the same, if I take a point like this one, this is saying that p of, if that's 2 or something, that's saying that p of 2 plus p of 0 equals 0. But then it would also be true, so x is 2, y equals 0 is the solution. But then it would also be true that over here, p of 0 plus p of 2 is equal to 0. I mean, we've just worked out that that statement is true, p of 2 plus p of 0 is 0. If that statement's true, then the point 0, 2 should also be on the curve. But it's clearly not in this picture, right? This picture doesn't have symmetry reflection in the line y equals x. So not this curve. This cannot be the sketch of this curve for any polynomial p. So not A. Yeah, not A. Not this option, because that includes A. So that leads me to C as my answer. C and D can be done, but not A or B. I was suspicious about B because of the sharp corners. In fact, B can't be done with a polynomial for a reason a bit like this. Thinking about what would be happening along these straight edges of this triangle. So, for example, here along this line, we'd have lots of examples of points along here where p of x, so x is fixed, p of y constant, so p of y is constant, it's taking the same value for lots of different y. That's not something that polynomials do, unless it's the 0 polynomial or something. Polynomials have zeros. Polynomials have roots. They don't have a section where they're constantly 0 for a bit. That's just not how polynomials work. If your polynomial's degree 10, then it can have at most 10 real roots. You can't have a section of the real line where your polynomial is just constantly flat. What would its derivative be? The derivative would also be 0. What's its 10th derivative? Also 0. That's a problem for a 9th degree polynomial, and so on. Right. Okay, so this is impossible. You can't have straight lines like this. You have to think about something like that, because this curve does have symmetry in the line y equals x. So it's not ruled out by the argument that we ruled out A. It's ruled out by a different argument. But in fact, the options that we've got for this mean that we don't really have to think about B unless we want to. Okay, my answer is C. This question is about transformations of the plane, which is perhaps not something familiar. It's not really on the maths syllabus as something that you've already seen about, but we hope that by defining things like this, functions with inputs and outputs, that we can sort of do some basic operations to combine those things together and think about what happens, for example, if you do one of these functions and then another one. I suppose it's the point of this question to try and understand these complicated functions or transformations. Okay, so the question asks us to calculate TS and ST and to show that those things are not equal to each other. So these are, each thing here is a transformation of the xy plane. This one's made by doing S first and then doing T. There's a sort of inside-out notation going on here where you do the inside thing first. That's what this is trying to explain. And the one on the right is you do T first and then you do S. and we're going to show that those transformations are not the same thing. Okay, so let's track what happens if we do s then t. So I'll leave the t alone for now, and I'll write down what s of xy is. That's x plus 1 y. So I've taken s and I've applied it to xy. The way to do that is you add 1 to the first coordinate. Okay, now I've got to apply t to this thing. The rule for t, well, it's written out here in terms of x and y. I think I should imagine these being sort of dummy variables. This is just showing me what happens when I have an input here and an input here. It takes my first input and puts it over here, and it takes my second input and it puts it here with a minus sign. So watch out for that. Okay, what I'm saying is this is minus y x plus 1. So it might be slightly confusing that this application here uses a sort of different meaning of x to this meaning of x up here. If it helps, you can think of this in terms of other letters of the alphabet. You could imagine t of uv is minus v, u. If that helps imagine this application of t to different coordinates. Anyway, this is what happens when you do s then t. Let's find out what happens when you do t then s. So I'm going to apply t first. That's going to give me minus y x. And then I'm going to apply s to this. That'll give me minus y plus 1 x. Okay, and the question is, show these things are not equal. I mean, they're obviously not equal, right? This one, they've got different numbers going on. If I had to prove that these transformations are not equal, I think I would maybe check what ts of 0, 0 is, and check what st of 0, 0 is. Check a particular input. That's one way to show that two functions are different, show that they've got different outputs for the same inputs. Ts of 0, 0 is 0, 1, and st of 0, 0 is 1, 0. So those are not the same points, so these functions can't be equal. Okay, that's part 1. Part 2 is interested in what happens if we do t, this transformation, lots of times. And the question asks, sometimes you do t a bunch of times and you get back to where you started. When does that happen? For what values of n? This notation, it's explained in the question, is supposed to mean you've done t n times. Okay, so my approach for this is just to work out what happens when you apply t multiple times. So we've seen that t of xy is minus yx, that's given in the question. Let's work out t squared of xy. Well, so that will be apply t once and then apply t again. So the rule is always you take the first coordinate that you're given and you write it in the second place. So here I'm going to write minus y there. And then you take the second coordinate you're given and you write it in the first place with a minus sign. Okay, so that's t squared. And then if I apply t again, I'll get, well, so take the first coordinate and write it in the second place. And take the second coordinate and write it in the first place with a minus sign. I'm still not back to where I started. If I do t 4 times, then I'll get, you take the first coordinate and you write it in the second place. And you take the second coordinate and you write it in the first place with a minus sign. T to the 4 of xy is xy. So n equals 4 is one example of this. But actually, so I could keep working out t to the 5, t to the 6, t to the 7, t to the 8. I'm not going to write those on the screen because I've spotted that now that I've got back to where I started, if I do t 5 times, that's like doing nothing and then doing t once. Because t to the 4 got me back to where I started, and the answer to this is in fact going to be t n equals 4 or n equals 8. If I go round this pattern twice, or n is any multiple of 4. Okay, so 4, 8, 12, that sort of thing. So t has this kind of periodic behaviour that you go round these points. There's some geometrical interpretation to these, by the way, that maybe it's helpful to think about. S is a translation. It takes points in the plane and translates them. T is actually a rotation. I don't think you need to spot that to do this question. You can do this question with algebra, like I've done here. But t has this kind of periodic behaviour because it's a rotation by 90 degrees. Right, okay, part 3. In part 3, we're asked to use s and t to build this transformation, which is called u. U is supposed to be the transformation that subtracts 1 from your first coordinate. Translation to the left, I suppose. Let's remember s of xy was x plus 1y, and t of xy was minus yx. Okay, so the challenge is to build this out of those transformations. So I'd get going messing around with bits and pieces of these. I suppose when we were doing t lots of times, I saw some minus signs coming up, so I want to try and exploit some t's. I think it's clear that if you just use s, then it's pretty obvious what happens if you apply s lots of times. You add 1 each time, so you'll end up at x plus 2, y, and so on. So we're going to need some t's in there as well. But it's a little bit tricky because t is going to swap the x, and t swaps around the x and y's. I suppose if I add 1 now, if I do t first, and then I do s, I add 1, then I've got a 1 minus y, which I don't really want at all. I don't want it after I've shuffled around, and I definitely don't want 2 minus y. So doing s next feels bad. But maybe if I do t twice, see, that gets me to minus x minus y, and that's looking a little bit more promising because now I can do an s, and I'll get a 1 minus x over here, which is not quite what I want, but it's better than having a 1 minus y, because this 1 minus x is minus x minus 1. Okay, so I'm messing around, but I'm trying to mess around in a sensible direction. So s, that's right, x, y in here as well. So my plan is to do an s next. That's going to give me 1 minus x minus y. And now what I really want, is to flip both of these, put minus signs in both of these again. Actually, I've seen that's what t squared does. T squared puts minus signs on both the first argument and the second argument. If I gave this a name like v or something, that would be the transformation put minus signs on both. So what I really want to do next is t squared s t squared. That's going to be x minus 1 y, which is u. So u is equal to t squared s t squared. Great news. The question also asks, what's the least number of applications of s and t in total that can produce u? And here I suppose that's suggesting that there are maybe other ways of making u. I suppose I could have messed around with some more powers of t. There's no point having 6 t's because that'll rotate me around and then get me back to the same thing as doing t squared. So I'm quite happy that I've only got t squared in there, not t to the 6 or something. Is it possible to do with fewer? Okay. So we must have at least one s. We've seen that just powers of t doesn't do it. Powers of t we worked out in part 2. So you must have at least one s. Sorry, we must have at least one s. We must have at least one s, and then I've got to think about how many t's I want. And after playing around with it for a while, I realised that it doesn't matter what you're doing with the s's. The coefficients of x and y need to be 1 and 1. That only happens if you do a multiple of 4 t's. So I need a multiple of 4 t's. You can write that argument out more clearly and with more reasoning in it to say, well, look, as a kind of extension of the thing we did before, applying t lots of times, we saw this kind of characteristic pattern of minus signs appear in front of x and y. And actually, if you do some s in there, it just adds on a number. It doesn't change the coefficients in front of those x and y's. So we need a multiple of 4 t's just to get back around to something with 1x and 1y, no minus signs there. S doesn't change those coefficients. I think that's an important point. There's a geometric interpretation here that t rotates the xy plane, and u is supposed to be a translation. It's not supposed to rotate the plane at all, so we need a multiple of 4 of those rotations by 90 degrees to get the plane back to the right orientation. That's if you want to do this with geometry. Okay, maybe not the sort of geometry that you're used to thinking about. Okay, algebra also fine. Right. Part 4, show that for any integers a and b there is some sequence of applications of s and t that maps 0, 0 to ab. Okay, so a and b are integers. They could be positive, they could be negative. Maybe we should think about positive cases first. I like breaking down these problems into different cases. Because I can already see that if I apply s lots of times, I can get from 0, 0 to, so if I do sort of s of a, of x and y, is something like x plus a y. So s of a of 0, 0 would be a 0. Just by thinking about what happens when you do s lots of times, I can see that applying s lots of times is going to give me some map that takes the origin 0, 0 to a0. Okay, that's pretty good. I suppose I could use u lots of times. So this is if a is positive. If a is negative, then I could do u to the a. U to the minus a. If a is negative, then u to the minus a is saying do u a positive integer number of times of xy. That's going to be x minus a y. Okay, right. So that's how I could get to. So that would take the origin to minus a0. So I can get to any point along the x-axis just by using s and u. I suppose the challenge is then, can I get to other points without a 0 there? I'm probably going to need to bring t in, aren't I? What happens if I do s a times and then I do t? So I'm experimenting by bringing in just one t. I could think about maybe doing t first. But if I do t first, that takes the origin to the origin, so I'm not too excited by that. T keeps the origin where it is. And it's a rotation around the origin. Right, so s to the a followed by t is something that I think is slightly more interesting, because that's going to take me to minus y x plus a. So t of s to the a of 0, 0 is 0a. And now I'm getting onto the y-axis. Similarly, so this is if a is positive. If a is negative, I could do this to get to 0 minus a or something. This was probably a, wasn't it? No, I've got confused. What do I mean? 0, 0. Let me think very quickly, sorry. X minus a. If a was negative, then I wanted to do u a times to get to x. Excuse me, this was a plus sign all along over here. And so was this. There we go. There we go. Put some minus signs back in. Yes. U subtracts 1, and I'm doing it minus a times. Very confusing. Okay, maybe not worrying about negative signs too much. I've now got some way of getting to the y-axis for positive or negative a. I'm not done. I'm sort of regretting doing a first, because now I want to do a translation again. Now that I've got up to the y-axis, I've got a map ready to go that does translations in the x direction. So I think what I actually want is t of s to the b xy. This is my next idea. It's x plus b. That gets me to 0b, and then s of a t to the s of b xy will give me b minus y x plus, or excuse me, a minus y x plus b, which will get me to ab. That's if a and b both positive. If they're not, if they're 0, ignore that step. S to the 0 is no transformation at all. If a or b is negative, use u instead. And I made a little bit of a mess of the calculations above, but you'd use u just instead of have to translate in the opposite direction, either for the a or for the b. Okay, that's part of 4. That's how you get to the point a, b. Part 5 defines this parabola. It's got the equation x squared plus 2x plus 2. I really want to complete the square on that. I'll give it a minute though. It asks us for the equation of the curve that happens after we apply the transformations to the curve. So we've got to think quite carefully about what it means to apply the transformation to C. I suppose it means apply it to all of the points on the curve. So if we had a point, if xy is on the curve, or I suppose on C, then after S, x plus 1y is on the new curve. I don't have a name for that. I'm not going to give it a name. C2 or something. C prime. C with a C, yeah, let's go C prime. Okay, so I've got to find out what this new curve is. They give me an equation for the original curve, so I can go and work out the coordinates of points on this new curve. I'm being really careful here because it's quite tempting to just stick in x plus 1 instead of x and leave y alone, that's actually a translation in the wrong direction. That's actually not how this works. It's a little bit like that problem where a translation to the right means you put a minus sign in your equation for the transformation of a graph. It's a little bit like that problem. That's why I'm being careful not to write down this. That's actually in the wrong direction. I'm going to show you why in a moment. Okay, so if xy was on the curve, then actually I can say a little bit more about that. If xy is on the curve, then y was actually equal to x squared plus 2x plus 2. Okay, that was the point on the curve before on C. So now we've got x plus 1, x squared plus 2x plus 2 is on C prime after doing S. It's the x coordinate that's got translated. Okay, I need to find an equation for this new curve. I think the best way to do this is to give these things new names. I could go x prime and y prime for my prime world after transformation coordinates. Might be a little bit confusing. I'm going to go with u and v instead. So if I write u is x plus 1, and then this thing here, and v is x squared plus 2x plus 2, I want to find an equation relating u and v, so I'm going to substitute in. Okay, do you see this? So x is u minus 1, so when I substitute in, I actually get my equation for the curve has minus signs in. It's been translated to the right. That's where these minus signs have come from. And this is not what you would get if you just wrote down replacing the x's with x plus 1s. So there's a little trick going on there. This is my equation for the curve. I'm going to multiply out some brackets, I think, to get u squared. There's two u's cancel, I get a 1. I take off 2, so I'm going to get u squared plus 1. Minus 2 plus 2, yes. U squared plus 1, which I suppose I could write. So u and v are sort of my new x and y coordinates. I could write that as y equals x squared plus 1 in this kind of new world for these new x and y coordinates. Okay, similar idea for applying t to c. So before we had x squared plus 2x plus 2 is on c. So after applying t, that point gets taken to the point minus x squared plus 2x plus 2 x. So this is, again, a sort of parametric equation for the positions of points on this curve. And it's not at all obvious what that's going to be. We can try and simplify this a little bit, I suppose. I could say, in my new world, if space, before it was the xy plane, if it's now the uv plane, then I've got u is equal to minus x squared plus 2x plus 2. I've got to work out the equation of this curve. So I'm going to do a similar process. I'm going to write u is minus x squared plus 2x plus 2, and v is x. Those are my coordinates in my new, I suppose, uv plane. That's my plane after doing the transformation. I'm giving these coordinates new names. I can't use x and y again because things will get confusing. Okay, so I'd like to plug that in. I'm going to get, I suppose, u is minus v squared. I'm plugging in v this time, just felt easier to do, like this, which I could write, oh sorry, that's u equals on the left, like the previous line, u equals minus v squared plus 2v plus 2. Which I could write out in terms of x and y again. I could write x equals minus y squared plus 2y plus 2, but I think I'm going to leave it like that. There we go. Question 3 defines this function. It's defined piecewise, which means there's different values that this function takes in two different cases. We're asked to sketch this graph to start off with and then do lots of calculations to do with the gradient of the graph and comparing it to a cubic. Hint, it's not a cubic. Okay, so when x is positive, this is x minus 1 squared plus 1. That's a parabola, isn't it, with a minimum when x is 1 and this square is 0, as a minimum at 1, 1. Okay, let's draw that bit first. This is going to be my sketch over here. So up here, a minimum at 1, 1 quadratic. I guess it gets up to, what does it get up to over here? When x is 0, this is 1 plus 1 is 2. Welcome to the Oxford Maths live stream. And then when x is negative, it does something different. This quadratic has got a maximum when x is minus 1 at 3. And when x is 0, this is 3 minus 1 is 2. Okay, so this does join up in the middle. This is going to go up to some maximum. Not a great picture of a quadratic, but there we go. Okay, so quadratic over here, different quadratic over here. Both of them meeting at 0, 2. Okay, that is my sketch of this. Is there a point over here that I should be interested in? This is the point when x plus 1 squared is 3. I'm not going to work that out. It involves the square root of 3. I'm not interested, I think. Right, okay. Or I suppose I'm asked to go out to minus 3. What happens at minus 3? This is 2 squared. This is 4. 3 take away 4 is minus 1. So this is negative when I get out to minus 3. I'm not too interested in where it crosses the x-axis, I think. Right, okay. We're asked to write down expressions for m of x, so I need to go and read the question and find out that m of x is the gradient of the chord between 0 g of 0 and x g of x. Well, g of 0 I know now is just the number 2. That's okay, so x equals 0 is in both of these cases, which is a little bit unusual, but luckily both cases give me 2, so it doesn't matter which one I read when x is 0. Okay, g of 0 is 2. Okay. When x is positive, we're asked to find m of x in the case when x is positive. So I need to find the gradient of the chord between 0, 2 and x, x minus 1 squared plus 1, because that's g of x when x is positive. Okay, I know how to find the gradient of a chord. I'm supposed to write down the difference in y values divided by the difference in x values. X bigger than or equal to 0, I'm going to have m of x is equal to x minus 1 squared minus 1, that's the difference in the y values, divided by the difference in the x values is that. Okay, similarly, when x is negative, I'm going to work out m of x. Different equation for what that is. Again, I'm going to do the difference in the y values, minus 2, over, and then x minus 0. X minus 0 is now negative on the bottom, but that's still the expression for the gradient. Okay. Oh look, 3 minus 2 is 1, so this looks suspiciously similar, doesn't it? Let's write that 1 minus x plus 1 squared over x. Okay, that's my answer for 2. I suppose we should look at part 3 next. Show that, yes, I'm getting a little bit carried away. I've noticed some similarities between these expressions for m. It's quite interesting. I think we're gonna get there when we get there. So part 3, show that m of x plus 2 is x when x is positive. I suppose this was only the case for x positive, not 0. So over there, I've got an expression for m of x, and I want to add 2 to it. Well, that's going to be x squared minus 2x plus 1 minus 1 over x. If I bring in this 2, then I want to add on 2x to the top up here, and fantastically, the 2x's cancel, the 1's cancel, I'm left with x squared over x, which is x. Hooray! Okay, m of x plus 2 is equal to x. Does that mean m of x is x minus 2? I think it does. Maybe I should have simplified my fraction for m of x over here by multiplying out the square. Aha, okay. That's when x is positive. When x is negative, I've got to work out m of x. I think I'm still asked to work out m of x plus 2, so I'm asked to work out m of x 1 minus x plus 1 squared. I can already see the 1's are going to cancel. Over x plus 2 is going to be 1 minus x squared. Careful with all the minus signs. Minus 2x minus 1 plus 2x all over x. Which is equal to the 2x's cancel, the 1's cancel, minus x squared over x is minus x. Okay, so we found that when x is positive, m of x is x minus 2. and when x is negative, m of x is minus x minus 2. Okay, here's the punchy bit of the question. Explain why g has derivative minus 2 at 0. That maybe looks like it's come out of nowhere. This part of the question wants us to stop and think about what we're doing, what we've been asked to do. We're finding, you see, this gradient of the chord that joins x, g of x, to the point 0, 2. So as x gets close to 0, by differentiation from first principle, this should be getting close to the derivative of g. And we get the same thing if we come in from the left or if we come in from the right, because both of these expressions go to 0 as x gets really small. So these m of x, this is m of x plus 2. So if we subtract 2, we'll get m of x. Okay, let me write that out. So when x is positive, m of x is x plus 2. When x is negative, m of x is minus x minus 2. For small, x minus 2, I think it subtracts 2 from each side. For small x, these both get close. Both get close to, I've gone behind my head, both get close to minus 2. That's why g has derivative minus 2, because the tangent, the gradient of those chords gets closer and closer to the derivative of g at that point, provided they all go to the same thing. Right, okay, that's the derivative of g at 0. Great. Okay, part 5 brings in a cubic now. Suppose p is less than q and h of x is a cubic. It's got a maximum at x equals p and a minimum at x equals q. We're asked to show that h prime of x is negative between p and q. So I suppose this says show that the cubic decreases from its maximum to its minimum. I think several approaches to this. You could talk about how the derivative of h of x is a quadratic. It's 0 at p and q, that quadratic. Let's write this out. H prime of x is a quadratic. It's 0 at p and q. We can also think about the second derivative. Here we know the second derivative is negative at p because it's a maximum. The second derivative is the derivative of the first derivative. So this says that h prime is decreasing at p. So if I drew a picture of h prime, it would look like this, with roots at p and q decreasing at p. That means that h prime is negative between p and q. There are no other roots. It doesn't change sign. No other roots because it's a quadratic, so it doesn't change sign, and it's negative in between. Okay. Next part of the question wants us to think about a cubic with some more conditions on it. Suppose C and D are real numbers, and there's a cubic h of x with a maximum at x equals minus 1 and a minimum at x equals 1. So I suppose we're being given numbers for p and q. And we're told that the derivative at 0 is minus 3c, and the value at 0 is d. Show that c is positive. Well, hang on, that's saying we just proved that the derivative of a cubic between its maximum and its minimum is negative. So what do we know? We know h prime of 0 is negative by part 5. So minus 3c is negative. I suppose it's important that 0 is between minus 1 and 1. So minus 3c is negative, so c is positive. Harder part of the question, find a formula for h of x in terms of c and d at x. Okay, it's going to be a function of x because it's a cubic. It's going to have an x cubed term in it. Okay. We know it's got a maximum at x equals minus 1 and a minimum at x equals 1. I think I want to think about h prime of x. That worked well for me in part 5. I know that it's got roots at minus 1 and 1. So I know h prime of x is something like x minus 1, x plus 1, roots at plus and minus 1. There's some number at the front here. I just know that 1 and minus 1 are roots, so I don't know what this number is. I think it's going to have something to do with c. In fact, let's work that out. If I know that h prime of 0 is minus 3c, so let's plug 0 in, and I'll get minus a. Aha, so a is 3c. That's pretty good. So h prime of x, h prime of x is 3c. That's difference of two squares. This x squared minus 1. Okay, I want to find h of x. I'm going to integrate. I've got the derivative of h. Now I'm going to integrate up to find, oh goodness me, cx cubed minus 3cx plus a constant. But they've told me that h of 0 is the number d, whatever that is, some real number. Putting in 0 kills off these terms, so I want my constant to be d. Okay, that's my expression for h of x. It's a cubic, it's got turning points in the right places. Is it definitely maximum and minimum in that order? Yes, it is, because it's a happy cubic. Brilliant, okay. That's my expression for my cubic. Part 7 says, show there are no values of c and d, so this relates this to the previous part of the question, I suppose, such that the graphs of y equals g of x and y equals h of x are the same. So here's what we've been trying to achieve. We've got this cubic that had a maximum at 1, a minimum at a maximum at minus 1 and a minimum at 1, and we're comparing it to the cubic that we had before. Not the cubic before, comparing it to the graph we had before, which kind of looked a little bit like that, right? It had a maximum at minus 1 and a minimum at 1. Sort of definitely not a cubic, because it's made of two quadratics. That's not how you make a cubic. I think the way the question wants us to go is to think about c and d. There are other approaches you could take. You could say, look at x bigger than 0, where I know that g is a quadratic and h is a cubic. Those are not equal because those are not the same graph. Consider their like third derivative or something. H is a cubic, it's got some third derivative. G is a quadratic, it doesn't have a third derivative, or its third derivative is 0. So that might be one way to show that these quadratics and cubics are not the same thing. Let's try and engage with the question the way they might have had in mind though. Let's think about this graph. So, what would we want? We'd want C and D to match up with G, I suppose. We'd want everything to match up. Over there we saw that G of 0 was 2. No, was it 2? Yes, it was 2. G of 0 was 2, so we would want... we would need, if this was possible, we would need D to be 2. We also saw that the derivative at 0 was minus 2, so need C to be, what would C be? 2/3, so that the derivative at 0 matches on both these curves. I think I want to now try and show these graphs are different. I might check the value at 1 or something. I haven't thought about the value at that maximum or minimum yet. Check at 1. G of 1 we saw was 1, I think. Let's check back. G of 1 was 1, but H of 1 would be, well, so this would be 2/3 times 1 cubed minus, what is that? 2 plus 2. Excuse me, I've gone behind my head again. So 2/3 from this first term minus 3cx plus the d, I get 2/3. So these things don't match. These things are definitely not the same curve. Even if I choose C and D to make things work at 0, things don't match up at 1. So this cubic is not the same thing as the pair of quadratics glued together at the start of the question. Okay, that's question 3. Okay, question 4. This diagram looks terrifying. There's lots of stuff going on in here. Different parts of it are used for different parts of the question. So part of the skill here is to focus on the parts that we're being asked about and ignore irrelevant parts of the diagram. So there's loads going on in here. There's a point E that doesn't come into later in the question, and there's an angle X that we don't need to worry about yet. To start off with, all I think we need to know is that the centres are A and B, they're a distance of 2 apart, and the radii are √6 and √3 minus 1. Okay, let's read the first part of the question. So we're asked to find the angle CBA, which is the angle here between CBA. So I'm going to draw a separate diagram pulling out the relevant bit of this picture, which is going to be a little triangle with the angle CBA in it. That's the angle I want to find. And then on my small diagram I'm going to mark in the things I know. AC, what is that? So that's centre of the big circle, S1. So AC is the radius of the big circle, that's √6. And BC is the radius of the small circle, that's √3 minus 1. And AB is, we're told that's 2. Okay, so big complicated diagram. I've made a small simple diagram of just the bit of question I want. I want to find this angle, theta. And now I can relax a bit because although the big diagram is very scary, the small diagram is a triangle where I know all of the sides and I want to find an angle. That's something that you can do in a kind of routine way using the cosine rule. Slightly challenging to actually get the cosine rule right, so let's give it a go. It says opposite sides squared is b squared plus c squared minus 2bc times 2, so 2 times 2 times bc, 3 minus 1, cos theta. Okay, so I need to rearrange this and simplify to work out what cosine theta is, and then I'll find the angle CBA. Right, okay, so if I square this I'll get 4 minus 2 √3, and then I'm going to do some rearranging, so I'll get minus 2 plus 2 √3 is equal to minus 4 times √3 minus 1 cosine theta. So if I simplify that a bit more, I think there's a factor of √3 minus 1 on both sides. Here times 2 and here times minus 4, so cosine theta is going to be minus 1/2. I think that means that theta is 120 degrees. Okay, let's try and mark that in. So BC I'll draw in, 120 degrees. Fantastic, okay. Okay, it's quite a nice angle, given all these strange lengths in the question. Deduce that A and B lie on the same side of CD. Well, that's true because 120 degrees is bigger than 90 degrees, so this is an obtuse angle, and C is on the right-hand side of B. I think that's all you need to say for that. So CD is over there. It's on that side of B. Okay. Part 2 asks us about the length of the line CD. So I'm going to try and pull out the relevant bits of the diagram here. I suppose there's a choice, but now I've got this angle. I'm interested in the point B because I know the angle's there now. There's this symmetry up and down, so that I know this is 120 degrees as well. And I suppose that means that this is 120 degrees on the other side. So I've started to see this triangle where I know an angle, I know some sides, and I want to find the other side. I'm going to try and pull the triangle BCD out of this picture. What does that look like? It looks a bit like this. BCD. So we know this is 120 degrees by some previous work, and the fact that angles at a point add up to 360 degrees. We know that BC, that's still the radius of the small circle, and we'd like to find the length of the other side. So it's easy to jump into this and just say this is the cosine rule again, where now I know an angle at two sides and I want to find the other side. There's an alternative where because there's some nice symmetry to this picture, it's an isosceles triangle, we can chop this picture in half if we want to. I suppose, said differently, we could think about extending this line to where it meets CD. I think that might be slightly nicer because then we get to think about 60 degrees instead of 120 degrees. So I can do some trigonometry to say, oh, this is 60 degrees, so this side is √3/2 times as long as the hypotenuse, just by normal trigonometry. That's half the length of CD, So CD is 2 times that is root 3 times root 3 minus 1. If you multiply that out, that's 3 minus root 3. But it's also possible to use the cosine rule to find the length of CD. Let's give that a go now, just to practice using the cosine rule. That's going to say that the length CD squared is equal to B squared plus C squared is the same, minus 2BC cos angle, so it's going to be this BC, cos of 120 degrees is minus 1/2, so this will be plus. Okay, so I'll say that mod CD squared is going to be 3 root 3 minus 1 squared, so CD, if I take that square root, it's going to be root 3 minus 1. Length of CD is positive, which is the same as before. It's still root 3 minus 3. Okay, they would also like, so okay, so now we found the length CD as 3 minus root 3. They'd also like the angle CAD. I think it's clear which triangle I'm going to pull out of the picture now. I'm interested in the triangle CAD now, I think. Okay, what do I know about CAD? Oh, I know all of the sides, don't I? And I want to find an angle. That's cosine rule again, isn't it? Let's draw a picture over here. Hopefully this is not too bad. So I've got an angle here that I want to find. I've got side lengths AD and AC are both root 6. I know that CD is 3 minus root 3. I want to find that angle. Here we go with the cosine rule one more time. 3 minus root 3 squared is going to be 6 plus 6 is 12 minus 2BC is 12 cos angle. What am I going to call this one? I'm going to call this one alpha. Working my way through the Greek alphabet in a random order. So that's going to be 9 plus 3 is 12 minus 6 root 3 is 12 minus 12 cos alpha. Goodness me. 12 on both sides, that's good. I think cosine alpha is going to be root 3 over 2 minus sines and a factor of 2. I know that angle. That is 30 degrees. It's in this triangle, isn't it? Cosine is root 3 over 2. Okay, so this angle is 30 degrees. That's interesting. That's much smaller than it looks in the picture. This diagram's really not to scale. Okay, pretty good. We've now found some angles. Especially interesting, we found the angle CBD is 120 degrees, CAD is 30 degrees. Those are going to turn out to be useful in the next part of this question. And we know lots of lengths of sides now. Right, okay, on we go. Part 3 asks us about this shaded area. Inside circle S2 but outside circle S1. We're asked to calculate it and show that it's equal to some horrendous expression involving pi and the square root of 3. My strategy for finding the area between two curves like this is to think of areas involving each of the curved sides and do some sort of subtraction. It's a multi-step process here, I think, but I'm going to try and draw on some areas that I know the size of, involving the edges of this curve shape. So, for example, if I go around the outside, I'd like to make a statement about something that involves that side. It's part of the circle S2. You know, right, I've got to close this line up to make an area. Ideally, an area that I know about. I could go around the outside of S1, but I've no idea what that area is. Instead, this is part of the circle S2, so I'm going to join those ends up through A. Probably lots of choices, but if I join it up through A, then I've got an area that I know about, right? I know that this angle here was 30 degrees, so this is, I suppose, 1/12 of the... I've joined up to the wrong one. Part 3 asks us to find the area that's inside the circle S2 but outside the circle S1. That's the shaded region in this picture. We're asked to show that it's equal to this horrendous expression involving pi and the square root of 3. My strategy when I'm asked to find the area between two curves is to think about areas involving each of the curves and do some sort of subtraction. That's what I do on integration questions anyway. When I've got the area between two curves, I think about particular integrals and do a difference, like we did in question 1a. Here, the curves are parts of circles, so I think I'd like to think about areas involving circles. So if I draw this outside curve, that's part of the circle S2. I'd like to say something about some area involving that curve. I suppose I could join it up in lots of different ways. I could join it up to A, I could join it going around the outside of S1. I have no idea what those areas are. But if I join this up to B with straight lines, then at least I know what I've got. I've got that shape there is 1/3 of the circle S2. Okay. Of course, it includes this kind of blank bit over here as well, between C, B, D and this inside curve. So it's not quite the area that I want. I'm not really claiming it is the area I want. I'm going to do some subtraction. Okay, let's think about the inside line as well. Let's try and draw a different picture for something involving this inside line. Okay, so the inside line is part of the circle S1, so I think a sensible place to join it would be to the middle of circle S1. If I do that, then, well, that wedge I've drawn is part of the circle S1. I think this was 30 degrees, so that's sort of 1/12 of the big circle S1. Okay, things are coming together a bit. Annoyingly, I can't just do the difference of those two areas, because one of them goes to B and one of them goes to A. So there's a sort of extra kite-shaped area in between that I might have to think about. Or maybe I could split that as two different triangles. Yeah, I think I'd think about it like that. There's some area here that's inside both regions I've marked, some area that's only inside the blue area I've marked second, and some area that I want that's over there. Maybe I could do some inside-outside logic and make sure I count everything carefully. Something like that. Maybe I could split these up. Sometimes when I've seen areas like this, I've been thinking about the intersection between circles. The trick there was to draw in this line as well, which is helpfully already in this picture. If I draw in that line as well, then I've got this kind of wedge shape that's got a curved side and a straight side, and the other bit is a triangle. I think that might be a sensible way to split down this picture, because then I can talk about the triangles on one side. Actually don't want the triangles, do I? And I can talk about the wedges on the other side. And it's the difference between those wedge shapes that I want. Yeah, I think that's the way that makes it feel most like the difference between two areas. If I find the size of CD around the inside, and I find the size of CD around the outside, then the difference between those areas in some order will give me the shaded bit in between. Okay, let's try and put that into some sort of notation. So my idea here is I want this area going around the outside, including C to D. My plan is that going around the outside, I've got this kind of black area that comes down to B, and I know that overall that is 1/3 of the area of circle S2. This is not quite perfect notation, but I'm just taking notes at the moment. 1/3 of the area of S2, and I'm going to subtract that triangle BCD, this area over here. That will give me, I suppose, this sort of spotty area, we could call it, on the right hand side. I was talking about this being bounded by a straight line on one side and a curve going around the outside. Okay, that's one thing I want. And then I suppose I also want this area here bounded by a straight line and the curve around the inside. I'm going to give that a sort of crosshatch. And what do I know? Well, that's sort of bounded by my blue lines. So when I join it up to A, I know that I get 1/12 of the big circle. Okay, let's write that out. That's 1/12 of the big circle. 30 degrees is 1/12 of 360 degrees. Minus, I need to subtract, to get the crosshatchy bit, I need to subtract the area of triangle ACD. Okay, so my plan is to work out both of these and then do what do I want. I want spotty area minus the crosshatch area. Okay, that's my notes of what I'm going to do. So I'll actually do some calculations to see if I can get this expression. Okay, so spotty area is 1/3 of the area of S2. S2 has radius √3 - 1 squared times pi. pi r squared, 1/3 of that circle, minus, and then for the area of BCD, I'm going to use the fact that I know the radius BC and BD, and I know this angle. I'm going to use the half AB sine theta expression for the area of a triangle. What is sine 120 degrees? I think sine of 120 degrees is the same thing as sine of 60 degrees, which is √3/2. And that's going to be multiplied by √3 minus 1 squared for the length of those sides. Okay, that's my spotty area. I need to subtract the cross-hatched area, which is 1/12 of the area of S1. S1 has radius √6, and then plus, because I'm subtracting the I'm subtracting the cross-hatched area, and it contains a minus sign here. The area of triangle ACD, 1/2 of sine of 30 degrees. Same idea. Sine of 30 degrees is 1/2 of √6 squared. Okay, so let's try and simplify this. Let's do the terms involving pi first. I'm going to write those as pi over 6 because I'm aiming for pi over 6 out the front. So pi over 3, I need an extra factor of 2 so I can write this over 6 over a common denominator. That's going to be 2 times the square of √3 minus 1 is 4 minus 2 √3. And then I'm going to subtract this pi term over here, which is 6/12. 6/12 is otherwise known as 3/6. So that many pi over 6's. And I've also got, what have I got? 6/4 is 3/2. Subtract, what is this? √3/4 over 4. What is this? √3 minus 1 squared again is still 4 minus 2 √3. Okay, so looking almost there. Let's simplify the brackets a little bit. This first one is pi over 6 times 8 minus 3 is 5 minus 4 √3, looking good. And these other terms, I'm a little bit worried about this 3/2. That's not 3 at all. But I suppose I'm going to add on. Okay, so I'm going to add on 2/4 is another half of √3. Another half of a 3. So this is 3/2 plus 3/2, just about. And then √3/4 times 4 is √3. So I do get this expression, finally. Okay, but I think the important idea there was building this shaded area out of the difference of two shapes. I'm using the difference of this spotty area and this cross-hatched area. Okay, that's the area. Right. Last part of the question involves E and the angle X. Let's go. Here's part 4. Now we finally bring in the point E and this angle X. We're asked to consider the point over here is the intersection of some line with the circle S1. X is this angle. And we're going to try and find, well, not find, but write down an equation for the angle X so that this line splits the whole picture into 2 equal areas. Goodness me. Right, okay. So there's a lot to think about here. I think first I want to think about the total area. Right, I want the total area covered by S1 and S2. Okay, we actually know what that is because we just put loads of work into finding this shaded area, and the total area covered by S1 and S2 is the area of S1 plus that shaded area. So we actually know what this is. We know that this is √6 squared times pi r squared plus the thing in part 3. Go and write out the thing in part 3 and add 6 pi to it, I think. Okay, thing in part 3 was awful, so I don't want to copy it out right here. But we know that total area. Okay, what do we actually want? We want this line to split this into 2 equal areas. So I suppose I want the area on each side to be half of this. The area on this side is made of loads of bits. I just had a lot of work to find areas like that. I don't really want to try and find the area on this side of the line, bounded by straight line, weird curve of a circle that's centered on somewhere over there. But the area on this side of the line looks quite nice because it's made up of a big bit of S1 and a triangle. Let me show you. So if I draw in some lines, here's the area on one side of the line. So it's mostly made up of this big chunk of S1. That angle there is 360 degrees minus x. So this big chunk of S1 and a triangle, but we know about the area of triangles. Okay, so this area on one side is part of S1. We've got to think carefully about how much of S1 is over there, and I suppose it's 360 degrees minus x over 360 degrees, that much of a circle. So it's that much times pi r squared, that much of a circle, plus, and then I've got this triangle bit as well between A, E and C. That's going to have half root 6 squared sine x, I think, for the area of half A being sine x. Yes, okay. That's the area on one side. I want that to be equal to 1/2 of the total area. Okay, so I want 360 degrees minus x over 360 degrees times pi times 6 plus 3 sine x to be equal to 1/2 of 6 pi plus everything in part 3, which I still don't really want to write out. But that's what I want. Okay. And writing out that equation feels like too much work to fit onto this slide, but there's some horrendous expression that this satisfies with x's on the left and some constant numbers on the right. Okay. Explain why there's a unique solution x to this equation. Well, we could think very carefully about this equation and plugging in different values of x and looking for a sign change. Here I think I'd argue geometrically instead and say, look, what happens when x is a small angle and what happens when x is very large? Somewhere in between, you'll hit the sweet spot of having equal areas on each side. So I think I'd write down some argument to say, when x is 30 degrees, E is equal to D, maybe I'd work out that area, or maybe I'd just say that area is smaller than the area on the other side. Maybe it is. Yeah, I could plug in 30 degrees over here, couldn't I? I could work out 30 degrees. Check values. I check the values of these things, check whether that's half the area or not. I think it's probably not. And then check what happens if x is equal to sort of 360 degrees, I suppose. If x is almost equal to 360 degrees, if x is really big, this line goes all the way around until it's almost like dotted line up here instead of down there. Well, then it's pretty clear that the area on the left side is now really tiny. Check the values over there. That's getting pretty much 0 on this side for that angle on the left. Pretty much 0, and the right hand side it's some big number that's supposed to be half the area. So I think this is going to go from having too much on the left to having not enough on the left. Somewhere in between must be just right. So as we vary x, it will sweep around, that point E will sweep around from D around to C. It starts with too much on the left, ends with not enough on the left, none on the left. So somewhere in between, it'll be half. Question 5, this is one of the ones where we define some words and ask you to draw some pictures and work out what's going on. Here we define an n brick to be a rectangle of height 1 with n, and a tower is a stack of those bricks with some rules. Here's a picture of a 4 tower, and the rule is that in each level above something other than a 1 tower, you need to put 2 towers together so that the sizes add together, and they fit next to each other like that. Okay, so here 4 is 1 plus 3, 1 is fine, but then 3 we need to split down into 2 plus 1, and then 2 we can split down into 1 plus 1. So we end up with 1s, but each time we have to split the number down into things that add up to that number. Okay, the question asks us to draw the other 4 towers. Actually tells us there are 4 of them, which is nice. So other ways we could split this down. The first thing I thought of was, instead of splitting 4 into 1 plus 3, I could split it into 2 plus 2, and then I could split my 2 into 1 plus 1. Well, I sort of have to split the 2 into 1 plus 1. And then I was a bit stuck, because now we thought of splitting 4 into 1 plus 3, and we've thought of splitting 4 into 2 plus 2. And then I realised that you can have them the other way round. There's some symmetry going on, I suppose. Those count as different 4 towers. So we could have 4 and then stack on top of it 3 and 1 that way round. That's a different 4 tower. That took me a while to spot. Stacked on top of that, I suppose we could split 3 into 2 and 1 like that. But now I'm getting somewhere, because now I've realised that you can flip things around. I've spotted that when I split that 3 into 2 and 1, I was making a choice there as well. I could split it into 2 and 1 this way around. I've got 1 more to go, so I've done this the other way around. There were not really any choices in that one. I suppose I could take this one and flip a choice the other way round. So that was split 4 into 1 and 3, and then take that 3, and instead of splitting it in 2 plus 1, split it as 1 plus 2. You know, I think because addition is commutative, 1 plus 2 is the same as 2 plus 1, but you get different 4 towers for writing 2 plus 1 and 1 plus 2 in different orders. Okay, I found that last one a little bit leaning Tower of Pisa, but those are my 4 options for 4 towers. Okay, next part of the question asks for the maximum possible height of an end tower. You see, these ones have got different heights. This one's height 3, this one's height 4, just for how tall it is. So for the maximum possible height, I suppose when I broke down 4 into 2 plus 2, I felt like I was skipping out some numbers along the way. If I was being really slow about it and decreasing just 1 each time, then it feels like that will be the maximum possible height. Let me try and draw that and then think about whether that's right in general or not. So my plan is to split this down very gradually until I get down to 2, and then I've got to split 2 into 1, 1 and stop. Why is that the maximum height? Well, I've used the biggest thing on each level is the numbers 1, 2, 3 up to n. I can't repeat a number, right? I can't have n and then stick another n on top. You have to decrease the maximum size. So I can't hope to get any more than n. Okay, so it can't be more than n. Let's write that down. Can't be more than n, because max size of brick decreases as you go up. There's no way to get more than n levels, because 2 of the levels would have to have the same sized largest brick, which is not allowed. And we can achieve n using this picture on the left. Using a picture on the left. Okay, not very precise. I can explain what I'm doing. I'm taking 1 off each time. That is n, isn't it? 1, 2, 3, yes, n. Okay, that's the maximum height of an n tower. Decreasing the size of the bricks as slowly as I can, so as to get the maximum possible height. The next part defines the area. It talks about the sum of the widths of its bricks. I think that is actually the area of the pictures, because all the rectangles had height 1. So the area above was 4 plus 4 plus 3 plus 2 is 13. They ask about the expression for the area of an n tower of maximum height. That's the one I had before, where at the top it looks like 2, 1, 1, 1. And then below I suppose it was 3, 1, and it went down until we got down to n at the bottom. I suppose the layer above was n minus 1, 1. Okay, so let's try and read off the area of this picture. It's n at the bottom, then the layer above is n minus 1 plus 1, which also has total width n, and then the layer above, then it starts getting smaller, n minus 2 plus all the way down to 3 plus 2. Okay, so this is not quite the sum of an arithmetic progression because of this n. Sort of not the sum of the integers because it's missing a 1 and it's got an n. I'm going to be very careful. I'm going to write down the sum of the integers from 1 up to n because I know that sum off by heart. I'm going to add on n for this bottom layer, and I'm going to subtract 1 because there isn't a 1 at the top of my tower. What is that sum? That's n squared over 2 plus n over 2 plus n minus 1. That's n squared over 2 plus 3n over 2 minus 1. Okay. Brilliant. That's the area of that picture that I had before. Part 4 asks about n such that there's an n tower of height exactly 1 plus log base 2 of n, which is a pretty strange thing to ask for. My suspicion here is the height is always a whole number, so is this a whole number? Is this an integer? 1 plus log 2n. I suppose if this is going to be a whole number, then I would need, I think, n to be 2 to the m for some m. If that's going to be a whole number at all, the height's got to be a whole number. If it is 2 to the m, then it's m plus 1 doing the logarithm. Is that good enough? Can I find towers with n is a power of 2 and height m plus 1, where the bottom brick is 2 to the m? Powers of 2 is making me think of that thing I did where I split 4 into 2 and 2. M plus 1. This is quite a short tower, isn't it? Because the bottom brick is really wide, 2 to the m, but the height is only m plus 1. So I think I want to get small really quickly. What if I split it in 2 each time? So if I split each brick, if I split each one in half each time, then I'll go down like this until I get to a row at the top that's all 1s. That's all 2 to the 0. The row below it will be all 2, which is 2 to the 1. The bottom row is all 2 to the m. So that's m plus 1 height, because of that extra row on the top that's all 1s. That's height m plus 1, and n is 2 to the m. So actually there is a tower. This is what I want, isn't it? This is an n tower. This is an n tower with height height 1 plus log base 2 of n, because that's 1 plus m. And I can do it for any integer m. So that's infinitely many examples. Infinitely many n, infinitely many m. N is just 2 to the m. Okay, and you need to split like this. Okay, those are my examples. I think that might be all of the examples where the height is exactly 1 plus log base 2 of n. Part 5 wants us to start counting how many of these there are, which is a classic thing to be asked for in a question where we've introduced something new and asked you to sketch a few pictures of them. Might want to know how many possibilities there are in total. And we're going to think about some sort of recursion relation to think about how many towers Tn there are in terms of smaller towers, which sort of makes sense because the tower is sort of built of smaller towers on top of it. You've got some choices about how you split down the tower into smaller towers. Let's try and think about that. So if we want Tn, the number of n towers, those are the ones that start with an n brick on the bottom. And then we've got choices about what we put on top. We could split n down into a 1 brick and an n minus 1 brick. Or we could split it into 2, n minus 2. I'm trying to work through the cases systematically. When I was working out the 4 towers, I sort of did them in a random order. But here I'm trying to think about all the cases of what could be going on, or ... or you could have a really wide brick n minus 1 over here and just 1 on the right. Okay, so those are my choices. Let's think about the possibilities. So in this case, I've put 1 on the left, and I've got an n minus 1 brick, and I've got some sort of possibilities up here, but I don't want to keep thinking about those. I want to use the fact that that is Tn minus 1. That's the number of towers with an n minus 1 brick at the bottom. Okay, what's this? What are my cases over here? So I've got to put something on top of the 2, and I've got to put something on top of the n minus 2. I've got some choices, well, not really, there's only really one possibility, but I've got t2 possibilities for the stuff I put on top of the 2, and separately I've got tn minus 2 choices for what I put on top of the n minus 2 brick. Actually t2 is 1, so I'm making a big deal out of multiplying by 1. But these are sort of independent choices, what I do on top of t2 and what I do on top of the n minus 2 brick. Okay. Over here, I've got maybe quite a few choices for what I put on top of the 3 brick, and I've got really quite a few choices about what I put on top of the n minus 3 brick. But using the notation of the question, that's the number t3 times the number tn minus 3. Okay, so I want to add these together because these are alternatives about what I do. So choosing how I break down that brick, those are alternatives, and I should add my cases for those. But once I'm in one of those cases, the choices about what I do on each of the 2 bricks are independent, so I should multiply my choices within each of those cases. Okay, so I should do this sum. I suppose I should put maybe a t1 in here. Okay, so I've got a big sum, adding together lots of products of things. Lots of cases. In each separate case I've got independent choices. I'm going to add those up for all my different cases. Okay, my formula is tn is t1 tn minus 1 plus t2 tn minus 2 plus dot 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 plus tn minus 1 t1. Okay, use my formula to calculate t6 is the question. So we know t1 is 1, t2 is going to be t1 squared, which is also 1, t3 is going to be t2 t1 plus t1 t2, which is 1 plus 1. 1 plus 1 is 2, welcome to the Matt live stream. That makes sense because the 3 brick gets split into a 2 on the left or a 2 on the right. T4 is T3 T1 plus T2 T2 plus T1 T3, which is 2 plus 1 plus 2, which is 5. That's encouraging. We had 5 possibilities in the first part of this question. T5 is going to be T1 T4 plus T2 T3 plus T3 T2. Oh, hang on. So there's a bit of a pattern going on here, isn't there? Because T1 T4 is the same thing as T4 times T1. I can just work out these first 2 terms and double them. Okay, I'm going to do it like that. T1 T4 is 1 times 5, and T2 T3 is 1 times 2. So this is 14. And then T6 is going to be T1 T5 plus T2 T4 plus T3 squared plus T4 T2 T5 T1. Okay, so 2 of these. So I should work out 2 of T1 T5, 14, plus T2 T4 is 5, plus T3 squared is 4, which is 19 times 2 is 38, plus 4 is 42. Okay, so that's T6. Brilliant. And I kind of spotted along the way that when I was working out odd numbered ones, I got this kind of, the terms came up twice, so it was even. And when I was working out even numbered ones, there was this kind of leftover square bit on the end. This T3 squared only comes up once as I go through all of these terms. In the last part of the question, we're asked to show that Tn is odd if and only if T2n is odd. And maybe you could check the first few terms of that sequence that we just worked out to see whether that's true or not. The observation I want to make is that T2n, this thing about terms coming up twice, T2n is T1 T2n minus 1 plus T2 T2n minus 2 plus and so on until you get to Tn Tn, and then you get the previous terms again written in the other order. As we come back out again, we're going to end up at T2n minus 1 times T1. That's the first term again. So it's this. This thing with the 2 out the front is even. So we've got T2n is this even thing plus Tn squared. Okay, we've got an even thing plus Tn squared. So I suppose I could say T2n is odd if and only if Tn squared is odd. Okay, because if this thing on the left is supposed to be odd, well, I've got a big even chunk over here. I would need Tn squared to be odd, because even plus odd is odd. Even plus even would be even. I don't want that. Okay. Final part of the argument, I suppose, is that Tn squared is odd if and only if Tn is odd. I need to check here. Odd squared is odd. Odd times odd is odd. Even squared is even. Even times even is even. So Tn squared is really only odd if Tn is odd. And it is odd if Tn is odd. Right, okay. So putting all that together, I've got T2n is odd if and only if Tn is odd, which is what I'm asked for. Hooray! That's the end of question 5. Question 6 is about writing fractions in a particular form as the sums of reciprocals of distinct positive integers. We're given an example. 4/5 is 1/2 plus a quarter plus a 20th. Okay, we're asked to write the following numbers as the sum of reciprocals of distinct positive integers: 2/3, 2/5, and 23/40. Right, okay. Let's give this a go. So 2/3 is, I suppose it's bigger than 1/2, like this was. So maybe I should try throwing in a half. What's my leftover bit? This is 4/6, this is 3/6. So this is plus 1/6. And that is in friendly form because it's the sum of 2 and 6, which are distinct positive integers. Okay. 2/5 is less than 1/2. Maybe I should think about 1/3. Is it bigger than a third? It's bigger than a third. Maybe I should take off 1/3 and go from there. What do I think? So this is 1/3. This was how many 15ths? This was 6/15ths. This is 6/15ths. This is 5/15ths. So my leftover is going to be 1/15th. Okay, fantastic. I've spotted 2/5 is 1/2 of 4/5. So I could take the expression they've given us and divide it by 2. 1/8 plus 1/40th. Should have thought of that quicker because then I wouldn't have had to do any work. Right, okay, last one, 23/40. That is going to be, it's bigger than a half. So I'm going to write it as 20/40 plus I've got 3/40 left. Is this going well? Well, I've got 3/40 left. I think that's, I think it makes sense to write that as 2/40ths plus 1/40th because 2/40th is a 20th and then I've got 1/40th left over. Okay, great. I've written all of them in friendly form. That's part 1, to practice writing numbers in friendly form. Part 2 asks us about subtracting 1/m, where m is the smallest natural number, so that 1/m is still less than q. Subtracting that and looking at how the numerator gets smaller when you do that subtraction. Okay, so a lot to take in here. They've told me that q is a/b, and I sort of just want to plug that into the other statements they've given me. I think I'll start by thinking about this condition that I'm told. See, I'm told that, so I'm given that 1/m is less than or equal to a/b. I suppose everything's positive, so I can say that b is less than or equal to am. Okay, fair enough. What's this thing? M is the smallest natural number such that this is true. How can I turn that into maths? I suppose if I made that number smaller, then this kind of sequence of fractions, as I make the number smaller, the fractions get bigger. M is the smallest possible natural number, so that 1/m is smaller than q. So it must be the case that this one is bigger. It's too big. It must be bigger than q. Okay. 1/m is smaller than a/b, but 1/m minus 1 would be too big. It would be bigger than a/b. So that would say that b is bigger than am minus a. Okay, so putting those together, I think these together say that am minus a is less than b less than or equal to am. Okay, putting those together gives me these kind of bounds on b in terms of a and m. I don't know if those are useful. That just feels like what I've been told about m. Okay, so somewhere between a times m and a times m minus 1. Right, okay. multiples of a somehow involved. Okay, looks good. Right, what do I actually want? I want to think about, so now think about a over b minus 1 over m. I've got a lot of AMs around, so maybe I want to write this as one fraction. I suppose I'm going towards writing this as C over D, so maybe I want to write this as AM minus B over BM. I don't know if that's in lowest terms or not. I'm told that C over D is that fraction written in lowest terms. Are there any common factors in there? I think maybe there could be. It's not obvious that there aren't. Maybe it's the case that this is, so when you take out a factor to write something in lowest terms, the numerator and denominator both get smaller. Maybe this is already smaller than a. If this is already smaller than a, then I'm done, because this is a way to write that fraction with a smaller numerator than a. And maybe it's the case it's not in lowest terms, so it'll get cancelled out. I'm a bit confused by this in lowest terms. But maybe this is already small enough. Okay, is that true? AM minus B. Aha, yeah, so this is a statement involving AM, B and A. And if I rearrange it a little bit, it says AM minus B is less than A. So yes, okay, AM minus B is less than A. Right, okay, summary. We're given, maybe this bit was irrelevant, we're given 1 over m minus 1 is bigger than A over B. By the way this is set up, m minus 1 would be too small, 1 over m minus 1 will be too big, be bigger than A. And you can rearrange that expression to say that AM minus B is less than A. That's important because then when I subtract 1 over m from A over B, I get this new fraction. The numerator in this new fraction is AM minus B, which is smaller than A, and then C is going to be less than AM minus B, because I'm going to write this in lowest possible terms. Lowest possible terms, it can't get worse than this. I'm going to take out some common factor from top and bottom. C will be less than AM minus B, which is less than A. I suppose C could be equal to AM minus B. But C is going to be smaller than A. Okay, great. I've shown the thing that I was asked to show. 3 tests whether we can see what to do with that. So taking any rational cube between 0 and 1, can we express it in friendly form? So my plan here is to use, at each stage, at each step or something, m such that it is the smallest, integer with 1 over m less than or equal to q. Like in the previous part of the question, I've tried to write out what it said in the previous part of the question. I want to use the smallest possible m at each stage such that 1 over m is less than or equal to q. I know that if I do that, the numerator gets smaller each time. So each time I do this, the numerator gets smaller. The numerator started at some value and it's getting smaller each time, so this is going to be finitely many steps. So finitely many steps. This process will end once I've reduced that. Once I've reduced that numerator down to 1, I suppose. So that's my plan. I need to check. So that's going to finish in finitely many steps because I'm going through that process, making the numerator smaller. I need to check that it's distinct reciprocals, which is a bit of a pain. So I suppose we can think about, I suppose 2 of them are the same. So I suppose at some point I took off 1 over m, and then later in the process I took off another 1 over m. It sort of feels to me like I wasn't being greedy enough early on. I could have taken off a larger chunk. Yes, so back here when I subtracted the 1 over m, over here I know this leftover bit, if it's including a 1 over m later on, I could have subtracted 2 over m by taking off both of these 1 over m's at once. That would have been a bigger. I mean, that's not a 1 over fraction, but maybe if I write that sort of 1 over m over 2, and I guess I want to sort of roughly m over 2, I want to round it up a little bit or down a little bit. That's a smaller number. Smaller number that I could have subtracted. Smaller number I could have used back in that earlier step. I've been greedy. I've been using the smallest possible number each step. So I should have done better over there. Need to tidy this up a little bit, of course. Part of this argument is, I suppose, I need, let's say, so roughly m over 2. I'm being a bit cautious because what if m's odd? So if m is even, consider m over 2 earlier. If m odd, consider, I suppose I need to think about m over 2 plus 1 over 2. m plus 1 earlier. Is that actually less than m? So there's sort of lots of little bits to check here. Is that actually less than m? Because I've added on a thing now, haven't I? Is that actually less than m? That's less than m if m is, yes, I think it is. It's less than m if m is bigger than 1. Yes, if m is bigger than 1, which it is because all these fractions, I mean, the number starts between 0 and 1, so all the fractions I'm considering are going to be smaller than 1. Okay, good. No repeats in my expression. Demonstrate my procedure by finding a friendly form for 4 over 13 is the next part of this question. So I need to think about the biggest fraction I could subtract from 4 over 13. I think that means 4 over 13 is smaller than a half. Is it smaller than a third? How big is 4 over 13? I suppose I could think about 13 over 4. I'm thinking about reciprocals here. 13 over 4 is about, it's somewhere between, isn't it? It's somewhere between 3 and 4. So 4 over 13 is going to be somewhere between 1/3 and 1/4. I think. Have I got that right? 3 and 1/4. It's somewhere between 3 and 4. So this is somewhere between 1/4 and 1/3. The procedure says I should be subtracting the biggest possible bit I can each time. So I'm going to write 4/13 is 1/4 plus something over 52, I think. So this was 16 over 52. This is 13 over 52. So this is 1/4 plus 3 over 52. And look, this numerator has got smaller. Quick check, if I've written it in lowest possible terms, but even if there was a factor of 3 there, it would just make the numerator smaller. Okay, I've got to do this again with 3 over 52. 52 over 3 is somewhere between 17 and 18, isn't it? Because 51 is a multiple of 3. It's 17 times 3. So this is somewhere between 1 over 18 and 1 over 17. So I subtract 1 over 18. And then write, oh my goodness, I've got to write something over here. I'm not really looking forward to working out this fraction. Wish me luck. So what's that? That's 4 times 13 over here and 2 times 9 over here. So I should put both of these things over something like 4 times 13 times 9. So I should multiply this one by, goodness me, get these all over a common denominator, right? So this is 3 times 19 over 4 times 13 times 19. I don't really want to work out that number yet. And I'll write this 1 over 18, 2 lots of 9, 26 over 4 times 13 times 9. I've got to do a lot of subtraction now, haven't I? Definitely 26. So 2 and 13, 26. Over here, 4 times 13. I'm multiplying up by 9, not by 19. So this is 27, this is 26 over 4 times 13 times 9. So this is 1. 27 minus 26. I've got to work out this number, I suppose, which is 13 times 36. Off we go. 3 times 36 is 108. 10 times 36 is 360. So this is 468. My goodness. Okay, so 4 over 13, following this procedure, is 1 over 4 plus 1 over 18 plus 1 over 468. My word, there we go, in friendly form with the friendliest of numbers. Last part of the question says, assuming that the sum of these numbers increases without bound as you add more and more of them up. So as we make n really large, we're adding in more and more terms into this sum. This is the sum 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus and so on and so on and so on. As that sum gets, as you add in more terms, so 1 over n. So as you add in more terms, we're told that this increases without bound. Maybe that's surprising, maybe that's a fact you already knew, or maybe not. Either way, we're told it in this question. We're asked to show that every positive rational number, not just the ones, I think before we had the ones between 0 and 1, look, not just the ones between 0 and 1 can be expressed in friendly form. So my first thought here was, okay, maybe we write this, any other rational, positive rational number, we could write as a kind of whole part, and a leftover part, like 2 and a fifth is 2 plus 1/5. So if I could make 2, then I already know how to make 1/5. Problem is I don't know how to make 2 using fractions. I can think of some ways to make 1, like 1 is a half plus a third plus a sixth, but actually it's a little bit tricky to think of ways to make 2, and if this was like 22 and a fifth, then I've got to think of a lot of ways to make 1. This sum doesn't feel like to me it's going to give me whole number parts, so I need to be slightly more clever. But let's take the spirit of what we were doing before. Before we were just being greedy and taking the biggest chunk that we could before. Let's do that here. Let's say let's try taking n large as possible, so that we've still got the sum from 1 up to n of 1 over n is less than or equal to q. Okay. So in particular, this thing plus 1 over, in particular, one more term would be too many, plus 1 over m plus 1 would be bigger than q. Okay, that's too many terms. Now we've got a leftover bit. The leftover bit, we've got some distance to go between this sum. I've been greedy and thrown in loads of these fractions. I suppose the leftover bit, there's got to be less than leftover gap. There's got to be less than 1 over m plus 1. If the gap to q is smaller than bigger than 1 over m plus 1, then just chuck in 1 over m plus 1 as well. Keep going. Okay, so my leftover gap is less than 1 over m plus 1. A big m plus 1. That's less than 1. So I can write this leftover part. I suppose my leftover part, my leftover gap is q minus this sum. I can write, because the leftover part is less than 1, I can write this leftover part using previous procedure. Slightly worryingly, do I have to worry about repeating any fractions? I think no, because all of the previous fractions I've used are really large. All of the previous fractions I've used are bigger than 1 over m plus 1, and my gap is smaller than 1 over m plus 1. So I don't need to worry about any repeats. This leftover part is going to be, we'll break it down, it's smaller than 1, so I'll break it down with the previous procedure, and the fractions that I get won't match the previous ones, because the gap is small. The gap is so small that one more term would be too much. Yeah, that gap is somewhere in between, isn't it? Right, okay. So use as much of the sum as you can, and then do the last little bit using the procedure above, because it's only a small gap to go at the end. Okay, that's question 6. Okay, question 7. We're given a character in a video game. They're trying to collect magic coins by working their way up this cliff face. They start at the bottom corner, S for start, and they end at the top right corner, E for end. They get points for collecting coins along the way, but there's a condition. They can't go left or down, so they have to go up or right at each step. So if I start here, then I might go up, get this coin here, and then I could go up and get this coin, and then maybe this one, but then I can't go and get this one because I can't go left. So here I've got to go to the end, and I've only got 3 coins. Is that a good score? We're going to find out. The question is going to define 2 functions. One of them's C, it's got 2 inputs, I and J, and one of them's M, it's got 2 inputs, I and J. You could think of that like a matrix if you've seen matrices, or you can think of it as a function that takes 2 inputs, I suppose, like we've seen a couple of times on this math paper. The function is taking 2 inputs because the position is kind of in 2D, right? If the position is ij, then we're going to think about whether there's a coin there or not. You have to give it 2 numbers to let it know the exact position. Okay, maybe you could think of this as like a table, I suppose, of positions and numbers. Perhaps I'm over-explaining the idea of there either being a coin there or not being a coin there. Right, okay. The maximum score, Mij, is the maximum score you can get at that position. So it's associated with that particular position. I is greater than or equal to 2 and j is greater than or equal to 2. Okay. Describe how that can be determined. Oh, I see. Describe how that can be, this one, with I bigger than or equal to 2 and j bigger than or equal to 2, can be determined in terms of the maximum scores below and to the left. Okay. So, if you're here, and you're interested in the maximum possible score you could get while being here, I mean, really we're interested in the maximum possible score you could get at the end, but we've defined this kind of grid of values, M, I, J, the maximum you could have at this stage of the game when you're here. What's that got to do with the maximum you could have here or here? Well, because you can only go up or right, you must have come from one of these squares, either here or here. And being a greedy coin collecting player, you'd like to choose whichever one of those had more opportunity for getting coins. So I suppose I want the maximum I'd take. You see, if this was bigger than this one, I'd go this route. I'd go via this one. I'd work out how to get there separately, but if there's a way to get 10 coins and be here, then and only 3 over here, then I definitely want to think about that route with 10 coins. Okay, so I want the maximum of the notation's a little bit involved, but I want the maximum of these 2 numbers. That's m of I minus 1j and m of I j minus 1, and that's how I write my maximums. You could probably write that out with words if you like. Oh, there's a catch though, because I might actually pick up a coin on this square too. If there's a coin in here, then I get I pick up that coin as well. That increases the maximum as well. So I should remember to add on 1 if there's a coin here. That's the number Cij. It's 1 if there's a coin, 0 if there's not. Okay, so be greedy, take the maximum out of your 2 options of how you got to this point, and don't forget to add on 1, pick up the coin if there's a coin. Okay, that's my formula for m of ij. Something to do with the maximum from those possibilities, remembering to add 1. Okay. Part 2 asks us to use that relationship to fill in each cell to show the maximum score achievable on reaching that cell. So, because my formula depends on the values to the left and below, I need to work from the bottom left corner upwards. I can't start over here because I don't know these numbers yet, so I don't know the maximum of those ones. I want to get to the end, but I've got to start from the start. Okay. So the maximum at the start is 0 because you don't start with any coins. And then looking up here, I suppose there's only one way to get here. The first column and the first row down here are kind of separate cases, aren't they? Because you don't really have any choices. If you want to get up here, you have to go straight up. Okay, I suppose I can fill those in now. You have no coins if you get here. You have 1 coin if you got here. No coin. Sorry, 1 coin because you get to carry it with you. 2 coins, and then you've got 2 coins. If you go straight up, you go there. The formula we worked out was technically only for I bigger than or equal to 2 and j bigger than or equal to 2 because we were thinking about choices. Okay, right, filled in those numbers. If you just go straight up or you go straight across, now I've got enough to fill in some interesting values. In particular, I'd like to think about this one. Maybe it's not super interesting. My choices are 0 or 0. Doesn't matter which way I choose, I'm going to have no coins at this point. I don't even pick up a coin here. Right, similar logic. I'm going to think about the maximum value out of my 2 options. and I'm going to fill them in, kind of working upwards from the bottom left corner in this kind of diagonal. Okay, here, 1 or 0, I want the 1, and also I pick up a coin. Very exciting. I've now got 2 if I'm over there. I go the right way. 1 over here, and then I'm going to fill in this diagonal. So 1 or 2, I'd like 2, please. 2, 0, 1, I'd like 1, and I pick up a coin. 1 or 1, I suppose. 2 or 2, I'd like 2, 2 or 2, 2, 2, 2. Here, 2 or 2, it doesn't matter, but I'm going to choose 2 and pick up a coin. So 3, that's looking pretty good. 2 or 2 here, 2 or 2, 2 or 2, 2 or 2, but at least I pick up a coin. 2 or 2, 2. So now going along the top, there's not many choices going up, are there? Okay, 2 or 3. 3, 3, 3 here because I pick up a coin. 2, 3, 3. Over here, 3. Here, 3 or 3, and I pick up a coin. So 4, 3, 3, 3, 3. Here I've got 4 coins now, or only 3 if I go via here. I keep my 4 coins. Picking up a coin over here, so 4 over here as well. 3 and 3, I want 3. 4, 4, 5 up the top here. That's looking pretty good. 4 and 4, I want 4. 4 and 3, 4, and then 5, 4, 5. Okay, so my max is 5. And the next part of this question is going to work out how do you actually do that. So I've worked it along here. I haven't been keeping track of the actual route to success. The rest of this question is going to work out how to work out the route from this grid of numbers. Okay. Part 3 says, given an array of scores m, like I've got now, describe a method for tracing backwards from E to S to find a path that, if followed by the character in the right direction, would achieve the maximum score. Okay, so looking back at my grid, I want to look at this 5 and think, how did I get here? How did I get to 5? It wasn't by coming up through this 4, was it? So I'm going to work backwards. If both previous possibilities equal, doesn't matter. I suppose I could choose at random or choose the top one or something, choose to come from the left or choose to come from below. Otherwise, be greedy, choose the larger. Okay, so choose the one that gave me this many coins. Remember, this is a 5 because I was choosing the maximum each time. Okay, let's try and draw a route on here. So this 5, I could have come from here only, right? To get to the end. And now this 5 came from over here. At this point I've got a choice because it was 4 in either direction. I'm going to pick the top one. And this 4 could have come from either place. I'm going to go along the top. This 4 don't come from the 3. This 4 didn't come from the 3. This 4 came from down here. Here it doesn't matter because they're both 3. Here, this 3 didn't come from this 2. It came from this 3. 3 doesn't matter. It could have come from either of these. This 2 could have come from either of these. This 2 came from here. This 2 came from here. And then I'm going to come down here. Okay, so I've got a path that goes 1, 2, 3, 4, 5 coins. Okay, that's pretty nice. I like that. That's picked up 5 coins. Okay. Last part of the question asks, how many possible routes were there? It wants a method for computing that. So I suppose I like working backwards here. I like working backwards and thinking about keeping track along that route of how many possible paths there were. Every time I've got options, I want to keep track of those numbers as well. So I suppose I could draw in a kind of grid of possibilities. So this, for example, this 5 could have come from a 4 over here. Yes, it could have come from a 4 over here. This 4 could have come from here. This 4 could have come from here. There's kind of this lattice grid of places where I could have come from. If I try and draw all the possible routes, this 3 would have had to come from this 3, but then this 3 could have come from down here, avoiding those zeros, but this 2 could have come from either side. This 2 could have come from the 1, and this 2 could have come from here, which... so that's my grid of possibilities, and then I want to count backwards through this grid, counting how many possibilities there were. So there's one way starting here, one way here. Here there's one way to get here, working from end to start, but then I'm going to think about reversing all these routes. There's one way to get here, going along and then down, one way to get to here, but then there's 2 ways to get to here, because I could go either from this 1 or from this 1. I'm adding the numbers together. One way to get to here, but then 3 ways to get to here, either coming via this 1 route from above or via either of the 2 ways from this side. And I'm going to keep working backwards, so this is 3 ways to get to, 3 ways here, 3 ways here, then 6 ways that I could get back to here, working backwards. And then over here, I suppose 6 ways here, 6 ways here, something massive like 12 ways over here, 6 ways to get to here. I need to work down, so 6 ways to get to here, 18 ways to get to here, 24 ways to get to here, so down here 24 ways to get back, and then I'll reverse all of those routes. So my method is to draw on all of the links from one place back to all of the previous possibilities, and then label those with numbers, adding together all the possibilities along the way. I suppose I could fill in some zeros in the rest of this grid because they're not viable routes, and then I'm adding up the previous numbers, working from top right to bottom left until I've worked out the routes. That's my algorithm. It's slightly different from the one in the web solution, which starts from the bottom left and works upwards. There's more than one possibility for this. Okay, that's question 7.